I want to talk about some stuff which I'm working on at the moment. So I just started a brand new project, um, which I'll tell you about in a few moments. So I'm basically exploring the space and trying to think of ways where we can make advances. So I'm quite excited about this. So it's really nice to give this talk here. So the plan for today, or the plan for the entire course, there might be, depending on how quick we go, I might add some stuff, maybe 2 more points here tomorrow. So this is the plan. We're going to spend some minutes talking about sort of AI, safety and trustworthiness issues, and some future research challenges associated with this, of which I see this work that we'll talk about as one particular small part. Okay, then we're going to have a little bit of maths. So I'll talk a little bit about some basics of probability theory. And just out of curiosity, can you put your hand up if you have studied some probability theory before? Okay, nobody. Good. That's good. That's good because I'm going to do it in a slightly different way to the way it's done usually. So I'm going to do it from my own perspective, which is a little bit different to the way you would learn it at the traditional course in probability theory. So these two parts, part 2 and part 3, are going to be kind of mathsy. So please keep trying to stay awake for these 2 parts, because later we'll make everything much easier. Okay, so if you survive until part 4, then things will get much easier, and we'll have some fun, right? So hopefully we'll do some modeling. So I've got one prepared, one very cute puzzle that we're going to solve together using these techniques, and there are several more. So if we have time, we can continue and have some fun tomorrow. Okay. So let's begin. So I want to talk about AI. So I guess everyone here knows that AI is very much the thing that's extremely hyped up at the moment. And it's actually, it is for good reason. AI applications are already shaping decisions in high-stakes applications. So educational attainment. We know that students are using ChatGPT. I don't know if they use them here in Cali, but but the funny thing is that what we don't tell you is that a lot of professors are also using ChatGPT to mark, right? So and give feedback. So eventually we'll just take all the humans out of the loop, and the entire university can be run by ChatGPT. So banks use AI. So for example, because obviously, AI, the whole concept of machine learning is based on analyzing huge amounts of data and drawing statistical information out, right? So banks are interested, for example, in, you want to loan from me. Are you the kind of person that's going to pay back the loan? Right, and then by analyzing data associated with you, these AI applications will say yes or no. Right, so there's a lot of people in Europe who are very uncomfortable with this. So, for example, we've just passed in Europe this brand new law in the European Union called the AI Act. And one of the principles is, for example, that if an algorithm makes a decision that affects your life, you should be able to get an explanation of how this decision was made. So employment decisions, again, these are things like CV screening. AI applications are used for these purposes. Healthcare, sort of for analyzing X-rays, analyzing patient data, patient history to make clinical decisions or to help clinicians diagnose. Criminal justice. So this is also, AI is used to decide whether a prisoner should be paroled. Okay, so these are all quite high stakes applications, right? We want to be able to make some guarantees about these things. We want to understand, or at least have confidence that these things work. And in the near future, we also know that AI will power safety critical autonomous systems like safe driving cars, robotic surgery, and getting more and more, as we go down this list, things get a little bit darker. So things like, the use of AI targeting in combats, etc. So there have been examples of this in recent months. I don't want to get into it because it's quite depressing. And there are some people also that are quite afraid of this concept of AGI, which is this artificial general intelligence. And this is the idea that, companies like OpenAI, companies like Meta, Google, they're really racing to construct this thing. So the idea behind AGI is that you really make something like a general superhuman intelligence. Okay, so essentially you can just replace people with AI. And there's a, who's heard of X risk, existential risk? Okay, nobody. So this is something quite maybe niche, but something that it seems like several people are very worried about. So some people are worried about that when we reach AGI, these superhuman intelligent machines will decide that actually, probably for us, it's better if we just got rid of the humans, right? Because, we're made of metal and oxygen is not so good from metal. So let's just pump all the oxygen out of the atmosphere. It's going to be better for us. Exactly. So this is why I put the picture. Yeah. So I'm not going to talk about this kind of stuff in this tutorial. I just wanted to give you an idea of the kind of spectrum of things that people are discussing and people are worried about. And clearly, maybe some of this stuff here is still a little bit science fiction, but a lot of this stuff is already being used, right? And in particular, as I said, I live in Estonia, which is a small country, but it's a country that kind of has as its own brand that they really want to be technologically advanced. There's so much hype, AI is going to solve all our problems, but how confident can we be that these things actually do what people who sell them claim they do? Okay, so some issues about trustworthiness. So what is trustworthiness? How can we, what should happen in order for us to trust AI? So for me, trustworthiness is really the intersection of three different things. Okay, so it's correctness, it's security in the sense of cybersecurity, but also privacy, preserving privacy, and ethical, responsible deployments. So I'll very quickly go through this. We're not going to talk at all about security. We're not going to talk about responsible deployment. This tutorial will mostly be about techniques to talk about correctness. Okay, so correctness is concerned with things like how accurate or robust is the solution, right? So does the AI application do what it's claimed to do? So one funny example of robustness is in Estonia, in the winter, we have a lot of snow. Right? So sometimes there's meters of snow. And there's an Estonian company called Starlink that makes these little robots that drive around in the city. And the idea is that this is like, the concept is this last mile delivery, right? So let's say you order a pizza, maybe the pizza delivery service drops it off at the central pickup point, and these robots drive around in the last few hundred meters to deliver your pizza. So these robots are always driving around town, but in the winter they always get stuck in the snow. Right, so they're not very robust. But this is why, like, it's an interesting, engineering is a very interesting field, right? Because it's not enough, because the starting people are quite brilliant, and they're brilliant because they made these robots extremely cute, like, so they're very sweet looking things, right? So whenever they get stuck in the snow, you see like a old Estonian grandma walking along, and the grandma will like pick up the robot and like pat it on the back and take it out of the snow, right? So this is social engineering, right? It's evil. We cannot let the machines win like this over us, right? So I personally, I never help them, right? I laugh, I go, ha ha. So this is like robustness, right? But we also need to, as we roll out these AI applications, we need to be able to understand risk, the kind of risk that's involved, and how to verify performance guarantees. I don't really want to talk about this very much because it's not really a focus of this tutorial. But security consists of things like being able to get into the training data, right? So let's say I'm developing an application for a bank that's going to help the bank decide whether to give loans or not to certain people, right? If I'm a malicious actor, then I can just poison the data and say, if your name is Pavel Sobocinski, you can have all the loans you want, right? So that's to do with data poisoning, but also logic poisoning. So you can actually change the learning algorithm to do what you want. And of course, one of the things that's always a problem in machine learning is privacy, right? Because machine learning is all about huge amounts of data. And where does the data come from? Well, the data has to come from the real world, concerning real people. So actually, there was an article published in Nature just in the last few days, where they studied what happens to machine learning, to learning algorithms, when they learn from data produced artificially, so produced by other AI. And what happens is very quickly there's a collapse, right? So very quickly you get nonsense. Okay, so machine learning really depends on real data, and often, for example, in large language models like ChatGPT, there's been cases where you can trick the algorithm to reveal some of its training data, right? So that can reveal information that shouldn't be revealed. So the last thing is ethics. So just to get back to things like the regulation space, AI can be used for all kinds of very nefarious activities, like deepfakes, like bullying, like spying on people. So, I mean, there's a very different philosophy, for example, between using AI in Europe, in America, and in China. So China is one of the world's leaders now in artificial intelligence, but China used it to essentially make China a very high-tech police state. Right? So in China, they use AI, have very advanced facial recognition software. They have cameras basically in many public places. So the state just basically keeps track of all its citizens, right? So it's kind of very scary. It's definitely not something that Europeans want. So yes, so this is sort of like the ethical issues. But let me talk about, from now on, we're mostly going to concentrate on this correctness aspect. So I want to talk a little bit about the state of the art, right? So when you have companies like OpenAI, like Google, like Meta, when you have they're huge companies, $100 billion, trillions of dollars companies that are investing billions and billions, hundreds of billions into AI right now. So one of the, because the investment, the private investment is so huge, it's in the interest to make very bold claims about how safe and how good these products are. Right. So let's go through some of the things that actually get done in the industry right now. So essentially, the two models that are used in practice are something called reinforcement learning through human feedback, and red teaming. And both are basically based on having a small set of users who interact with the model, try to get it to do bad things, and eventually, if they they sort of patch the system enough so that these users can't get the model to do something which is deemed bad, then this is now called safe, right? So these are really this is like taking this is like to me as a computer scientist, this is something like using sticky tape to fix a car crash. Like it's extremely disappointing, and I certainly don't trust it at all. Right? So the first thing is it's completely not scalable. Right? It's these things are the models that are being produced are now extremely big. Right? So the amount of data that's being fed into the learning process, the amount of parameters that these neural networks have, there's no way that you can throw enough resources at these kinds of techniques to make them scale. But it's also the kinds of the kinds of methodology that's being used here. It's all about trying to search for problems, right? So, but let's say I pay you to test my application for a week and try to get it to try to tell me if you can get it to do something that it's not supposed to do. If you don't find it after a week, what can we conclude, right? What kind of guarantees can you give me? Well, you can't really say anything. I mean, maybe if you spent 1 more hour, you'd find something. Also, there's a problem in that especially something like reinforcement learning from human feedback, the model itself then tries to learn how to make the tester happy, right? And sort of this is known as something as specification gaming or reward hacking. I don't want to get too much into this, but essentially my main point here is that the current techniques that we have are very questionable. So I have this quote here by Joshua Bengio. So Joshua Bengio is a professor in Canada, in Montreal, who is one of definitely one of the most, if not the most famous AI researcher in the world. He has a very nice blog, so I encourage you to check out his blog. And this is from his blog, I pulled it. So he wrote, unlike methods to build bridges, drugs, or nuclear plants, current approaches to train frontier AI systems, the most capable AI systems currently in existence, do not allow us to obtain quantitative safety guarantees of any kind. Right, so that's kind of a worrying state of affairs. That's something that we will need to fix. And this is something that I want to talk about today. I mean, this is what this tutorial is about. So I want to talk about sort of modeling probabilistic systems. We're going to talk a little bit about diagrammatic calculi, and the idea is that in the long run, this will give us tools to enable some kind of a more principled, rigorous way to test AI systems. So I want to spend just a little bit of time talking about current research agendas. So there's one big research project going on right now. It's called AI 2050. It's a 125 million 5-year investment by Eric Schmidt, who is the ex-CEO of Google. And this research program sort of analyzed 10 big questions that need to be solved in order for AI to be a benefit to humanity. Okay, and out of these 10 questions, the first one is about the sort of scientific and technological limitations to enable further progress in powerful and transformational AI. This is really, the current work on frontier models that researchers at the big companies are doing, right? So the hard truth is that universities don't really do this stuff very much. And the reason why universities don't do this stuff very much is that as soon as somebody does it, they get headhunted by OpenAI or Google or Meta and offered 50 times the current salary. And nobody says no to 50 times the current salary, right? So, so unfortunately, this research is being done in these companies. Ironically, the company called OpenAI, you think open meant open, right? But since about 2021, all of the research on frontier AI has gone dark. Right? So it used to be that they used to publish the algorithms. Google famously published a paper on transformers. But since 2021, they don't really let you they don't really let you see the algorithms, right? The papers, they do publish papers, but the papers are like press releases. They tell you about how much data they fed into the system, how many parameters the neural network has, and then maybe some, evaluation results like, does it pass these benchmarks, etc. So it's not a very nice state of affairs. But the good news is that that's just one question out of 10, and I think all of these questions are pretty good. And in particular, I think where university researchers can make a contribution is exactly in this area of safety and security, robustness, performance, and output challenges that may cause harm or erode trust of AI. I'm going a bit slowly, so maybe I'll skip the rest. But they're all very important questions, so I encourage you to look at this research program. So I'll tell you just very briefly about what I'm doing right now. So I'm part of this program called Safeguarded AI, Constructing Safety by Design. So this is funded by a UK research agency called ARIA. So ARIA is investing £59 million into this. It's starting next month, so 1st of September. So I've been very busy, trying to recruit people and organizing a research program. And the basic idea is that you want to introduce rigorous engineering safety measures as expected for critical infrastructure. So one thing that I didn't say before is that I think, how are we going to solve these big problems in the long run? So I think the kinds of things that I will talk about are only one tiny little part of the solution. I think what will happen is that you can look back in the history of humanity over the last, let's say, 150 years, at new technologies, so transformational technologies, how they were introduced and what happened, right? So one of my favorite examples is aviation, right? So aviation was introduced sort of at the start of the 20th century. They were the first people experimenting with planes. And at first it was kind of a free-for-all. People were building their own planes, people were crashing. It was very much of a kind of a, wow, let's experiment with this, let's see how far we go. Then you started getting the first commercial planes, and so people actually started using these, to travel. But again, there were a lot of crashes. There were a lot of problems with these planes. A lot of things were going wrong. But over time, you had this brand new discipline called aviation safety engineering emerge, right? And it's a really interesting discipline. So actually, I have to admit that one of my vices is that sometimes I watch on YouTube videos about plane crashes and the investigations, right? And it's actually really cool. I mean, I really like this field of AI safety engineering because it involves, of course, people thinking deeply about individual components and proving that they're safe using, for example, logical methods, formal approaches, engineering principles, so people who really do, do the mathematics, but also involves human factors, right? So things like, are the pilots talking to each other properly, or is there the communication between the pilots and the air traffic control done in a way that there's no confusion, etc. Right? And whenever there's a crash, what happens is you have a lot of investigators, and the investigators, they're not so much interested in assigning blame, right? So like, I think our natural instinct as humans is to say, okay, here the pilot was clearly, the pilot was at fault, right? It was the pilot's fault. Or was the air traffic controller's fault, or whatever. Like, we like as humans to say, it's your fault, okay, let's punish you and we can forget about it. Right? But that's not the approach of the safety engineering, of aviation safety engineering, because they really want to learn lessons, right? So they're not interested in blaming people. They want to establish guidelines. How can we learn from what happened to make this not happen again in the future? And I think we're going to see some of this evolve in a similar way for artificial intelligence. I think we're going to see a lot of horrible crashes, metaphorically, as well as not metaphorically, right? As soon as you have self-driving cars. But hopefully we can learn from that. And as I said, like the kind of formal approaches that we'll talk about is just one part of a bigger story. But this is a really cool program. So there's a lot of people around Europe who are going to contribute. And the idea is that at the end of the program, we need to show a compelling proof of concept demonstration in at least one narrow domain where AI decision support tools or autonomous control systems can improve on both performance and robustness versus existing operations in the context when the net present value attainable by full deployment is estimated to be billions of pounds. I don't know why that's important, but okay. Some examples of potential such early demonstration areas include balancing electricity grids, supply chain management, clinical trial optimization, and 5G beamforming subchannel location for mobile telecommunication networks. All right, so the idea is that it's a very ambitious program, and we want to construct both the underlying theory as well as applications of it so that we end up with a system which can make some guarantees about a behavior of an AI system. Okay, so this is now we're going to start getting a little bit more technical. I want to talk about sort of probabilistic reasoning. And for me, it's actually very interesting, right? Because in some sense, data analytics, machine learning, and AI are a paradigm shift for computer science. Because traditionally, the way I learned computer science, it was always Boolean reasoning, right? So Boolean logic, true, false, 1, 0, in, out, yes, no, right? There's no, you write if statements. You write, and if statements, the condition evaluates to true or false. It doesn't evaluate to maybe, right? But that's not at all how, machine learning, AI is about, right? AI is based totally on probabilities. The probabilities, some people joke, or partly joke, there's always a grain of truth in every joke, that AI is just a very hype name for applied statistics, right? And it's very much about statistics, it's very much about probability. And of course, we can't deny that it's useful, right? Because, for example, let's say if you're in some kind of a autonomous vehicle operations. So, for example, the Starlink robots that I talked about, I actually met the AI, the head of the artificial intelligence of Starlink. And he's a traditional computer scientist who also kind of then worked on artificial intelligence, worked on neural networks. And then the thing is that basically for some applications, traditional programming techniques just completely fail. Right? Let's say if you want to analyze something like a video and identify objects, there is no way we could ever produce a traditional program to do this, right? Like you could not write enough if statements to actually make this a reality. So here, machine learning, which is very much based on the statistical analysis probabilities, these are the kind of applications where it really shines. And of course, if you know a little bit about LLMs, the LLMs, the entire thing is really creating this enormous neural network, which is just a fantastically complicated engine for estimating probabilities, right? Because the actual run loop of an LLM, it's trivial, right? You could write it in 10 minutes. All it is just basically generate the most probable next token. So the next word. And obviously the interesting part is how do you tell what's the most probable next thing? And for that you have this enormous neural network that just estimates probabilities for you. Okay, so I've been talking for about 35 minutes. I don't like to talk for too long, so I want to maybe we can have a little question and answer session. So I have a few questions. So, what are your main concerns about the future development use of AI? Maybe what can we learn from how new technologies have been adopted in the past? I've mentioned aviation safety engineering, so I'll be interested to hear your thoughts. If anyone is brave enough to say something. Yes.
So regulations is a very European way to tackle things.
Yes.
And I want. Should I start working? So Europeans like to put regulations and things, and I wonder whether it is a concern for you that developing regulations and developing this sort of high stakes in terms of requirement systems might dampen development in terms of perhaps industry and giving the lead, for example, to the United States or China that might not have this type of restrictions.
That's a very, very good question. Yeah, thank you. So actually, I didn't talk very much about the AI Act, but I know surprisingly a lot about it. Surprisingly because I'm a theoretical computer scientist, but for last year, I've also become a part-time politician. So I had to give talks to many audiences which are completely non-technical, who are interested in things like regulation. And actually, the AI Act is I like it. Okay, so I think the people who put it together had precisely these concerns in mind, right? So they really want to protect developers, but at the same time protect the public. So one of the things is that actually the lack of regulation doesn't always promote innovation, right? So the reason why is that at the moment, you see that AI, the actual frontier AI development, is concentrated in 3 or 4 huge companies, right? So if you guys now want to go away and create your own system, you can't compete with the kinds of resources that these companies throw at the problem, right? So, and by the way, universities can't compete either. So just to train a frontier neural network, we're talking about $10 million just in electricity costs, right? So that's not research, that's not gathering data, that's not working on the algorithms. That's just what it costs to plug the thing into the power grid and learn, right? It's extremely expensive. So one of the things that the AI Act does is that if these companies want to push their software, sell the software in Europe, they have to share technical data with small and medium enterprises, right? So that the idea is that you let little smaller companies have a bite of this market, right? So I think that's a very nice thing. And in terms of regulation, in terms of banning or restricting things, so what I really like is that this law essentially breaks up applications into high risk, medium risk, and low risk. Where for low risk, basically there's no regulation. So low risk are things like, I don't know, like chatbots, use of AI in games. So basically things where, these things are not going to have any big effect on society. So medium risk are things like, education, medicine, the kinds of applications that we've talked about before, where essentially the companies just have to make an argument so that there's going to be some compliance mechanisms. And I guess no one really knows what these things are going to be like, but probably the idea will be that the companies just have to demonstrate that at least they're making some investment into making sure that these things do what they promise they do. And high risk are things like, deep fakes, cyberbullying, like just evil things, evil things that companies might want to use, might want to sell. I don't know who's sort of Cambridge Analytica here. Okay, a few people. So this was this extremely evil company in the UK which scraped Facebook data, basically trained some algorithms on this data to figure out how most efficiently influence people, especially to do with politics, right? So the customers included, several dictators in Africa, Trump, Brexit, like basically all of the terrible things. Okay, I mean, maybe you like Trump and Brexit. I don't know. I personally don't like Trump and Brexit. So from my point of view, a lot of the bad things that have happened in the world in the last 10 years, this company has had their fingers in it, right? So these things are clearly things where we need regulation, right? These people cannot be allowed to do this. So these are the kinds of things that are made illegal. So in my opinion, this is good. In China, they don't need to make regulations, because if the Chinese government decides that they don't like you, you just go and get executed. Right? So,
just disappear.
Exactly. And in America, well, you have these huge monopolies, because all these companies are American companies, so they can afford to influence the democratic process in America, right, by funding election campaigns, etc. Yeah.
How about the environmental regulation? Because we know that, like you said before, the development of AIs and everything, it has a huge cost in electricity and all these kind of things that can actually do bad to the environment.
Yeah. So I'm not entirely sure if the actual AI Act says anything about this in particular. But you're right. I mean, these things are extremely power hungry and not so good for the environment. I mean, the way they would spin this, let's say the AI companies would say, okay, so we're going to burn a lot of, we're going to use these 10 millions of dollars of electricity now, but then AI will become so advanced that it will help us to be more green in the future. Right? So it's so I guess that's the current mantra. Yeah.
In terms of cost, because you talk about how expensive it is to train an AI, that reduces the number of problems that I can really take advantage using AI. I mean, it's really expensive problems. The focus is going to be always in those expensive problems, or do you see like approach to make the training of AI cheaper?
Well, there's a lot of research. That's a great question. So at the moment, as I said, at the moment the frontier AI models, they are extremely expensive to train, and therefore only these big companies that are backed with billions of dollars of investment can afford to develop these models. There's a lot of research that's aimed at making it cheaper, making, for example, these systems more modular, right? So maybe you have some pre-trained base system on which you do sort of the final layer of training to specialize it. So there's quite a bit of research on this. I'm not an expert. I sit on panels that I have to read these grants. So that's my level of expertise. But we're not there yet. But I think that is a kind of a holy grail for especially university researchers, right? Because I think it's very, if you're an AI researcher at university, one of the very few ones who haven't been hijacked or headhunted by the big companies, I think it's very frustrating that you can't really do the top level research because you just will never be able to get enough resources, right? So for these people, it's very interesting to develop techniques that are more modular, that are more scalable. Yes.
Okay, so now that you mentioned that paper that AI actually performed really bad with synthetic data of other models, well, basically with fake data.
Yeah.
That's generated with
AI generated data. Yeah.
So there's also this theory, for example, in space, that if we leave a lot of garbage right there, we won't be able to ever get out of Earth again. There was all of this concern with Starlink, well, the satellites, because of that. If they crash, then we could get trapped. But there's also this idea that this could also happen in AI, because currently, with the introduction of all these chatbots, we're now getting a lot of slop articles that is just garbage.
Yes.
And it's very difficult to know which one is generated.
Yeah, exactly. We're poisoning our own data pool, right?
So how are we going to deal with that?
Wow. I mean, I think that's a really great point. I think that's, like at the moment, and it's surprising to me, it's surprising to me how many of my colleagues use ChatGPT. I hate this stuff, right? Writing is a creative process, right? And it's like going to the gym, right? If you never exercise, your muscles die. If we just start not using our brains and letting ChatGPT do all the work for us, then we'll just get stupider. And as you say, the more we use it, the more we poison our organic data sources with AI generated data. So it's all very worrying. I don't know. I don't have the answer of how to avoid the problem getting worse, at least in the short term. Yeah.
And is there any regulations or?
I don't think so. I don't even know how you would regulate it. I mean, so at the moment, one of the cute things is that at the moment, it's very easy. It's surprisingly easy to detect if a piece of text has been produced by an LLM. So there's some research groups. There's a research group in Stanford which specializes in this, and these guys claim that they can predict whether something's generated by an LLM to 98, 99% accuracy. So at least at the moment, you should be able to filter out this kind of garbage. And these are not very sophisticated techniques either. These are just kind of language analysis techniques. So at the moment, at least, we can protect ourselves from this, and this is why, for example, universities also now can detect whether students cheat using ChatGPT, because these things are still quite easily predictable. But of course, as LLMs get more sophisticated, they will try to hide this, right? Because that's not what they would like. But at least at the moment, I think it's still fairly easy to detect. Yeah, so thank you so much. This has been great. So I think we should maybe take a short break, 10-minute break, and then we'll continue with the next section of the tutorial. So thank you. Okay. Check themselves. Yeah. Thank you. Okay, so let's start on the slightly more technical stuff now. So we'll talk about some basic probability theory, but in a very different way to the way it's normally presented. So in particular, I'm using sort of four main sources here. The main source is this book by Bart Jacobs, who's a colleague of mine in Holland. The book is called Structured Probabilistic Reasoning. It's an incomplete draft. It's available online. So if you just Google that, you'll be able to find it. So yeah, but some other papers that are all quite recent, as you see. Yeah, I think I'll just move on. Okay, so this is part 2 of the course. So let's get started, right? So what's the simplest thing? I mean, the simplest example of something with probability, right? So it's something that we all know. It's throwing a coin. Right? So a fair coin will land 50% on heads, 50% tails. Okay, so we're going to introduce some formal mathematical notation, right? So the advantage of having a formal mathematical notation is that you can calculate, you can start proving theorems about these things. Okay, so following Jacobs, we're going to use a bracket notation borrowed from quantum theory. All that means is that we're going to use, we just described this process of throwing a coin, and the coin has a 50% chance of landing heads and 50% chance of landing tails. And what we'll write that as is this formal expression. So half heads in this funny notation, this is the kets. I don't expect you to know about quantum theory. It's completely not it's completely not relevant really, but just the notation is borrowed because it's a nice notation. So half heads plus half tails. Now this is not a sum. We're not supposed to calculate this. It's just an expression. Okay, it's just an expression that captures the possible outcomes of throwing a coin. If I throw a coin, then this is the stakes. Okay, so let's go through what this means. So HT, this stands for heads and tails. This is the underlying set of possible outcomes. And to this we associate probabilities. So probability in real life we talk about percent. Here we're going to talk about fractions of 1. And the idea is that all the probabilities together should add up to 1, or at most 1. So here, half plus half is 1. So half of the time we're going to get heads, half of the time we're going to get tails. And please stop me at any point if there are questions. Okay, so this is an example of a distribution. So in general, we're going to generalize this. So for our purposes in this course, finite sets are going to be enough. But in fact, this theory extends really nicely to infinite sets. Okay, so but for the purposes of this course, we're going to stick to the finite case, right? So we have a finite set of outcomes, x1, x2, up to xk. So what is a subdistribution? A subdistribution is a formal expression of this form, right? So this is just a general form of the thing you saw on the previous slide. So a1 x1 plus a2 x2 plus so forth until we get to the end, ak xk, where each ai is a positive number. It's greater or equal to 0. There are some really exotic theories where you can consider negative probabilities, but we're not going to consider those. And the idea is that we want all of them to add up to at most 1. So traditionally, in probability theory, you really want this to be equal to 1. But because we're computer scientists, we're going to allow ourselves a little bit of extra expressivity, and we'll see when we do some examples later that this is actually quite useful to let ourselves sometimes be below 1. So in the case where this inequality is strict, so the case where this is equal to 1 is just called a distribution. If it's less than 1, then we'll call it a subdistribution, or less than or equal to 1. So why are subdistributions useful? Well, you think of them as probabilistic ways of doing partial functions, and partially defined functions are very important in computer science. But this will become important later. So for now, I just want you to get comfortable with this concept of a subdistribution, which is just a formal expression of this kind. Okay, and we saw one example of throwing a coin. Okay, so we'll talk about, so there are all kinds of very famous distributions in probability theory. We're only going to talk about a few for the purposes of this course because, again, I want to just get to a point where we can do some cute examples and have fun. Okay, so if I give you a finite set, x1 to xk, the uniform distribution is just the thing where every outcome has an equal chance of happening. So if there are k outcomes, then each outcome has a 1 over k possibility of happening. Right? So this is the uniform distribution on this set x1 to xk. So we already saw one of these. So the result of throwing a fair coin is a uniform distribution on the two element sets, heads, tails. Okay. And similarly, if I have a die and I throw the die, if it's a fair die, then the outcome should be 1/6 as it comes out as 1, 1/6 that comes out as 2, 1/6 that comes out as 3, and so forth. Right? So this is the uniform distribution on the 6 element sets, the 6 possible outcomes of throwing a die. Okay, so that's all fairly simple, I hope. Are there any questions at this point? Please, if there are questions, yes.
Computer science was something a lot about ourselves to have probability distributions that not necessarily add up to 1.
Yes.
Which would be 100% probability.
Yeah.
But I wanted to ask you, what would be the meaning of the remaining?
Yeah, that's a great question. So we'll see we'll actually see examples of this. So I'll show you examples of this, but for now, the best way to think about it is that sometimes there's a failure. Okay, so let's say I have a coin that okay, I don't know if this analogy is going to work, but let's say this coin is made from porcelain and has there's a non-zero chance of it breaking as I throw it, right? So then maybe there's a 40% chance of heads, 40% chance of tails, and 20% chance that this will fail. So this thing that's missing from 1, we're going to consider it as some kind of failure. Okay, and and you'll see that this is actually quite useful to have for expressivity. So it comes up in lots of examples.
Like an unexpected catastrophe.
Unexpected catastrophe, or just maybe like sometimes, like for example, when you write a function, you want to make like an assertion that you assume something, right? Because you know that this function, whenever this function is to be used, you want to not have to consider inputs that you know will never be considered, right? So for that, you just don't even define the function. You just say assert this, and you don't even need to consider that case, right? So that you don't even define the function on those inputs, right? So it's basically just say, I don't care, I'm defined, I fail. Any other questions? Very good, but thank you for the question. Okay, so we're going to talk next about joint distributions. So if I give you two sets, x and y, a joint distribution is a distribution over the Cartesian product x times y. Does anyone not know what a Cartesian product is? Should I explain this concept? Who's never heard of it? Okay, very good. Okay, so Cartesian product, it sounds difficult, it's extremely simple. Frank should be teaching students about Cartesian products. What are you doing, man? So I'll give you the example that's on the slide. Okay, so a Cartesian product is just a fancy way of saying ordered pairs. Okay, so if I have a set of the possible outcomes of throwing a die, of tossing a coin, and here's my possible outcomes of the dice. Okay, then taking the Cartesian product gives me the set of all possible ordered pairs where the first component comes from this set and the second component comes from this set. Okay, so
It's kind of like combinatorics.
yeah, it's definitely combinatorics. That's all it is. So in probability theory, these things are really interesting or important because sometimes, let's say I want to throw two coins, or I want to throw two dice, or several things are happening at the same time, right? So there are several possible things that can happen, and we want to analyze the probabilities of several things occurring. And in AI, so machine learning, these things are extremely important, right? Because the whole reason why AI works is because we establish statistical correlations, statistical relationships between different factors. Okay, this is like the real thing. So this is all about joint distributions. You have this space of possibilities that can all happen at the same time, and we want to analyze how probabilistically they're related. Okay, so first we're going to look at a very simple example of this. So we take as an example the example on the board. So the dice and the coins. And let's say I do both. So first I throw the dice, and then I throw the coin. So the possible outcomes are going to be the Cartesian product of this and this. Okay, so it's just the same as on the board, but in the opposite order. So now the first element of the order pair will come from this set, and the second element will come from this set. And now we want to analyze the probability of the different possible outcomes. So what is the probability of getting a 1 on a die and a head on the coin? 1 or 12, right? So they're all 1/12. So this is the distribution now on the Cartesian product of these two sets, and it's called a joint distribution, right? Because we're talking about two different things happening. Now, in this example is very special and it's very easy in a sense, because these two experiments that we did, throwing the die and tossing the coin, are totally independent, right? They didn't depend on each other. That's why we get this 1/12. But the magical thing about probability theory is that sometimes joint distributions often describe much deeper relationships. Okay, and we'll see some examples later when we go through some key examples. Okay, so the next thing I want to say is marginalizing. Okay, so suppose that I have a joint distribution. So I have an example of one of these things that I did on the previous slide. So I have, let's say, a distribution of throwing a dice and tossing a coin. The idea of marginalizing is I can throw one of the outcomes away to obtain a new distribution on just one of the factors. Okay, and this is called marginalization. Well, I'll give you an example of this on the next slide. So I have a distribution on pairs, right? So this is just a compact notation for, let's say, the example on the previous slide where we threw a dice and tossed a coin. So we have one of these distributions. So the idea is that from this, we can get a distribution on just the x by throwing the y away, right? Like, let's say I'm only interested in the probability on the dice, and I don't care what happened on the coin, right? So I throw the coins away, the observation on the coin away. And that's essentially just basically means that I add up all of the probabilities for the y's for that particular x. And the similar thing is, you can do the similar thing on the y by marginalizing the x, right? So these are the mathematical formulas. They might look a bit intimidating, they're actually very easy. And you see this with the example, right? So let's go back to our example. This is the example of a distribution on throwing a coin and, throwing a dice and tossing a coin. So as we saw, we have a 1/12 possibility of each of the individual outcomes. Okay, so let's say that we only care about the coin and we don't care about the die. Well, what are the possible places where the h appears as a second factor, right? So h appears here, h appears here, h is going to appear 6 times, right, for each of the possible results of the die. Okay, so we just add up all of the probabilities for h, and similarly we add up all of the probabilities for the t, and so together we get half h plus half t, right? So we get half chance heads, half chance tails, which is not unexpected, it's what we expected. And similarly, we could marginalize the coin to only care about what happens to the die, right? Just by adding up all the probabilities. Okay, so it's called marginalization. It sounds very scary, actually, it's very simple. Are there any questions? Yes?
So basically, we can say that if we want to marginalize because the probability from a certain set of outcomes will basically just add up the probabilities related to that set.
Exactly. So, by the way, the reason why it's called marginalization is because you can think of these things as like, for example, here, you can think of these things as a matrix, because here, this is a two-dimensional thing. So I could just put in these probabilities in a matrix where, let's say here I put the dice as rows and the coins as columns. And in each, I put the probabilities. So in this particular case, we know that everywhere has 112. And now if I want to marginalize away the coin, well, I just sum across all the rows. If I want to marginalize away the die, I just sum across all the columns. And this now goes, but this is for arbitrary dimensions, right? So you can have, like, let's say, a three-dimensional thing where you have another dimension going in, and then this is like kind of the sort of geometric idea.
And this also responds to the question of how we implement these kind of calculations, for example, for an AI.
Yeah, so I mean, there's several different ways of implementing this. So we're going to see, actually, I want to get to the point. So we will, tomorrow, when we go through all the cute stuff, I'll show you some code that actually implements some of this. So there's some nice, because in the end, these kind of calculations, they get a bit tedious, right? So it's best just to let the computer do them for you and have fun with the modeling instead. That's what we will do tomorrow. But yeah, until we get to the fun stuff, we have to suffer through some more maths. So the next thing I want to talk about is products of distributions. And this is, we've already kind of seen one of these, well, we've seen examples of this before. So products of distributions is one way of getting a joint distribution. Okay, so products of distribution capture the idea of two independent distributions considered together. So if I have one distribution on x's, so a1, x1 up to a and xn, and another distribution on the y's, so b1 up to bn, yn, I get a joint distribution on the Cartesian product just by multiplying the probabilities. Okay, so this is, we've seen one example of this already. You know, this experiment of throwing a dice and tossing a coin. You could get the same sub-distribution, or you can get the same distribution here just by multiplying, you know, each of, this is has 1/6 probability, this is a half probability, 1/6 times a half is 1/12. Right? So this is an example of a product distribution. Okay, so this is a definition. Whenever you have a definition in mathematics, you need to kind of make sure that it works, right? So you have to make sure that it doesn't fail at the first hurdle. So first of all, there is some calculation here to do, right? So we've said that this is a distribution. We should make sure that if we add up all these numbers, they sum up to at most 1. Okay, in this case, it's a simple exercise, which we're not going to do. But if you want to get some practice with this, I really encourage you to verify that this is actually a distribution or a sub-distribution. So if both of these are distributions, then this will be a distribution. If both of them are sub-distributions, then they will be sub-distributions. But the question is, are all joint distributions obtainable by a product of the distributions? In other words, are all joint distributions the product of the marginals? Well, the answer to this question is no, right? Because products of distributions really capture this idea of two things being independent. But the really nice stuff, the really interesting probabilistic stuff, starts coming in when we have some non-trivial relationships between the different outcomes. Okay, good. So that's the idea of product of distributions. Next, I want to talk about sampling. So sampling exists in many programming languages with support for probabilistic computation. So if I give you a distribution W, so a distribution is just one of these formal sums, we can sample from it. So for example, consider the distribution half 0 plus 1/3 1 plus 1/6 2, right? So with half probability I get a 0. With 1/3 probability, I get a 1. With 1/6 probability, I get a 2. Okay, so this is this distribution. This just tells me something abstract about the chances of what happens when I run this experiment. But sometimes it's actually useful to run this experiment many times and see what happens, right? So programming languages have support for this. This idea is called sampling from a distribution. And for example, in Python, you can use this numpy.random library to sample 10 items from this distribution, right? So if you write, so multinomial is just another name for discrete distribution, which doesn't really matter. But essentially, we want to sample 10 items from this distribution. So this is just the way you would write the distribution inside of this library. So it's just a shorthand for this. And we get an array 5, 4, 1, right? So that means we've run 10 experiments by sort of running this experiment. And in this particular run, we got 5 zeros, 4 ones, and 1 2. Okay, but of course, if you run it again, you might get slightly different numbers, right? Because it's random. But it follows this particular distribution. So in particular, I'm not. So if we were to continue this tutorial further and go more into probability theory, of course there are important relationships between sampling and distributions, right? So if I sample for a long time, so maybe instead of 10, if I sample 1,000 or 1,000,000 or a billion, right? These numbers are going to get more and more close to a half, a third, and a sixth. Okay, and this is actually, in probability theory, this is a theorem. It's called the law of large numbers, right? So the idea is that the more you sample, the closer you get to the actual distribution. And by the way, calculating, so for the purposes of AI, calculating these distributions is really the most important and the most difficult thing, right? So you want to understand, you want to have good ways of calculating distributions. Like you want to calculate, a large language model, it's nothing but the underlying neural network. It's just a very complicated calculational engine to calculate probability distribution. And there are all kinds of techniques to how to calculate them, right? So of course these are very easy examples. Once these get larger, you need to have all kinds of computational tricks to allow you to approximate these distributions. Okay, very good. Are there any questions before we move on? Okay, so we're halfway through the mathsy stuff. So I just want to, so next we're going to talk about channels. And once we go through channels, then we can start giving final examples. Okay, so channels are what Bart Jacobs calls these things. I like the name channels, but in literature, they have all kinds of names, right? So maybe you've heard of things like stochastic matrices, Markov kernels, probabilistic functions. All of these really talk about the same concept. Okay, so we're going to talk now about things that are functions. So, a function typically is something that takes an element of a set. A function from x to y is something that takes an element of a set x and gives me an element of y, right? So if I have, addition takes 2 integers and gives me an integer. So what is a probabilistic function? Well, a probabilistic function is something that takes some element, and produces not an element, but a probability distribution. Right, so a function toss coin is a function that takes nothing, just takes a thunk, run, and then produces a probability distribution. So this notion of channel is going to be precisely this concept, going to allow us to talk about such functions. Okay, so let's give a formal definition first, and then we'll go through some examples. Okay, so let's Sx be the set of all subprobability distributions on the set X. Okay, so this is just going to allow us now to define a channel f from x to y to be just a normal function, kinds of functions that we know, from x to this set of distributions, subprobability distributions on y. Okay, so this can be seen as a possibly failing non-deterministic computation. And this is going back to your question before, right? Because for each x, I have to give you a sub-probability distribution on y, right? So that means maybe it's some computation that's going to give me some probability on an element of y, but this might not add up to 1. And that last remaining bit is this probability of failing, because this computation can fail. Okay, so let's just go through this bit by bit so we understand what it means. So all it means is that if I give you an element of x, of this set, then the result of applying f to x is going to be a subdistribution on y, right? So it's just going to be a subdistribution, which we've seen before, where all of the a's add up to be less than or equal to 1. And the intuition is there is a probability ai of getting a yi, and the probability 1 minus this whole sum of failing. So maybe some of you have heard of a Markov chains. So Markov chains is just the same thing as a channel from x to x. This is just for people who've heard this name before. I don't want to explain it. Okay, but anyway, I want to give you an example because this is a very important notion. This is going to be at the center of what we're going to do tomorrow in these probabilistic puzzles when we start solving them. So I want to give some examples. So my example is, suppose Professor Frank can be in 3 moods: angry, normal, or happy. His state of mind influences the probability of him giving marks, fail, pass, or distinction. Okay, so this can be described as a channel, let's call it M, from Professor Frank's state of mind to the set of marks. Okay, and I made up these probabilities, but possibly they correspond to reality. I'm not able to make that judgment. Okay, so what we need to do is we need to give a function from the set of the mental states to probability distribution on marks. Okay, so for angry, let's say, there's a half probability of fail, 1/3 probability of pass, 1/6 probability of distinction. For normal, maybe you're a bit less likely to fail, 1/3 fail, 1/3 pass, 1/3 distinction. So this is, let's say, maybe the fair outcome. And happy, maybe when Frank is happy, he's less likely to fail you and more likely to pass or give you a distinction. Okay? So that's an example of a channel. And you see that this is a channel that really gives us distributions, right? So all of these things add up to 1. So there's no failure here. Okay, so the interesting thing, the really cool thing about channels is that you can compose them. Well, you can compose them in 2 ways. So first I'm going to tell you about how to compose them in sequence. Okay, so given a channel f from x to y and a channel g from y to z, we can compose them to obtain a channel which I'm going to call f.g, so f followed by g from x to z. Okay, so technically, let's analyze what we need to do. So I have a function that takes a function f that takes elements of x to subprobability distributions on y. I have a function g that takes elements of y to subprobability distributions on z. And we need, for this guy to be a channel, we need him to be of the form x to subprobability distributions of z. Okay, well, what can we do? Well, we can take a subdistribution on y and apply g pointwise. So a subdistribution is this formal sum, right? If I just apply g to all the components, I'm actually going to get a function which I can call s applied to g from subprobability distributions of y to subprobability distributions of subprobability distributions on z. Okay, so this is a bit of a mouthful, right? So this is this animal, but actually there's a function called flatten, which just flattens out these probability distributions of probability distributions, just multiplies out all the probabilities to give us back a subprobability distribution. Okay, so now we can define this as f followed by sg followed by flatten, and this is now off the right side. So again, I don't really want to get into details. You can think about this later. I have an example of it on the next slide. But for now, I want to just say that this is associative. So if I have 3 channels and I compose them, it doesn't matter if I compose the first 2 first, then compose the third, or if I compose the second and third, and then compose the first, right? So, so if I have sort of F, G, and H channels, then if I compose F and G, and then H, it's just the same as doing this. So this is a very useful notion because it basically means we don't need brackets. So composition just makes sense. Okay, so let's go back to the example of Professor Frank. So suppose that Professor Frank's hunger influences his mood. Okay, so this can now be described as a channel F from the 2 states of being either hungry or full to angry, normal, and happy. Okay, so let's say that when Frank is hungry, there's a half probability chance that he's angry, and half chance that he's going to be normal.
So 0% chance he's happy when he's hungry.
Yeah, impossible. And when Frank is full, half chance that he's going to be in his normal mood, and half chance that he's going to be in his happy mood. Okay, so now we can compose F with M. So M is this, how Frank's mood influences his marking. And now we're going to obtain a channel from the set hungry full to the marks, right? So that kind of like hides away the middle. The middle bit is just the moods which are no longer important, right? So how is this going to work? Well, let's go through this. So the channel F then M of hungry, first we need to apply F, right? F to hungry. So F to hungry is just the state of mind. So this is the distribution of states of mind. Okay, and it turns out that because of the way this flattening thing works, I can just take out all the probabilities outside and apply M. So this is this channel we defined 2 slides ago. And now I just multiply things out, right? So I get half of what can happen when Frank is angry, which we know is half fail plus 1/3 pass, 1/6 distinction. So what happens when he's normal? And now if I just multiply everything and add it up, I get that in the state hungry, there's a 12% chance of a fail, 1/3% of a pass, 1/4% of distinction, 1/4 chance of distinction. And you can do the same calculation for full, right? And then once you multiply out all the probabilities, you get a quarter to fail, 5/12 to pass, 1/3 distinction. Okay, so you see now that this, by composition, we're no longer talking about somehow the state of mind, angry, normal, happy, has been hidden away, and now we have a probabilistic relationship between hungry, full, and the possible marks. Are there any questions? Yes. Yes. So by normal we mean adding up to 1.
Yeah.
Yeah, exactly. Yeah. So all of this works. It's if everything, if nothing fails, then the composition won't fail. Yes. Good question. Any other questions? Okay, very good. So I just want to talk about one more operation, which is a product of a channel. So there are 2 important operations on channels. One is sequential composition, which we just saw, and now we're going to see a parallel composition. So what happens if you just run the channels concurrently? Okay, so given a channel F from X to Y and a channel G from U to V, we can get the product channel F times G from X times U to Y times V. Okay, so now let's go through the particular. Let's again go through the definition just to see if we can construct something sensible. Okay, so again here, F is a channel, so therefore it takes elements of X to subdistributions of Y. G is a channel that takes elements of U to subdistributions of V. We need to, by doing the parallel composition, we want to get something from X cross U to subdistributions on Y cross V. Okay, so let's try to construct this thing, right? So elements of this guy, as we know, this is a continuum product. So elements are ordered pairs. So we have this ordered pair XU, and we're going to need to produce something in here. Okay, so let's see what we have around. Well, we have F, right? So we can apply F to the first component to get a distribution on the Y's. We can apply G to the second component to get a distribution on the V's. Okay, and now it's just kind of obvious what you need to do, right? So we just take the product, because this is a parallel composition, right? These things are not interacting, it's independent. So we just take the product distribution. We just multiply this distribution to get a distribution on the Cartesian product. Okay? So this is kind of like a non-interacting parallel composition. And tomorrow, because we're starting to run out of time, tomorrow I'm going to introduce a very intuitive graphical language for talking about these. And we'll see some examples. Are there any functional programmers in the audience? Anyone know Haskell or OCaml? Okay, good enough. So by the way, so maybe some of you know about the notion of monads. So monad is used in functional programming to capture sort of a notion of computation. So this is an example. So the sub-probability distribution is a monad, which gives the computational notion of a partial probabilistic computation, which is exactly what we're talking about. Okay, so channels are an instance then of a Kleisli map. Again, for those people who know what this is, you'll know. For people who don't know, it's just in the site that people know. I'm not going to explain this. And composition works in the same way as usual, because this flattening function that I mentioned is just the monad multiplication. And actually, the way product works, the thing that we introduced on the last slide, is also standard, because this is a particularly well-behaved monad, the canonical way of mapping of this type. Okay, so we know about channels, we know about composing them horizontally, composing them sequentially, and we know about composing them in parallel. So I'm going to spend the last few minutes today talking about special channels. So channels that we're going to use for modeling various examples tomorrow. So sub-probability distributions themselves are an example of a channel. Why is that? Well, because if we just take one to be the singleton set, so a set with just one element, then what does it mean to give a function from one element to the set of sub-probability distributions? Well, it means just to pick one, right? We just have to pick a sub-distribution, right? So a sub-distribution is just the same thing as a channel from 1 to x. Okay. Now, deterministic channels. Deterministic computations can be seen as special kinds of channels. So ones in which the probability of, if I just run a normal function, then the probability of obtaining the output is 1, right? So there are no non-trivial probabilities. So an ordinary function, fx to y, can be promoted to a channel. We call such channels deterministic. And it's very simple, right? Because if I give you a channel from x to y, I need to produce something of the form x to distributions on y, but I just take the trivial distribution that has the 100% probability of producing f of x, okay? So it's just a way of seeing ordinary functions as channels. Okay, so another special channel is called the identity channel. This is an example of a deterministic channel, and it's a very simple deterministic channel. Okay, so any idea of how this works? So what should the identity channel look like? So where should we take x? Where should we take little x? So the trick is in the name, right? Identity. It shouldn't really do anything. Yes, but it can't really take it totally to itself, right? Because it needs to produce a distribution. So which distribution should it be? Yes, it's 100% chance. It's just, and it's going to see in examples. It's extremely useful, right? So we're going to see, we're going to use it all the time. We'll solve some cool probabilistic puzzles, like the multi-hole problem. So I'm going to stop now. So thank you for your attention. And maybe we have 2 minutes for questions, if there are any questions. Is there a question? No? Yes.
Those checkers form some kind of group.
They form a symmetric monoidal category. So kind of related, yes, but it's because so it's this algebra of composition, right? You can compose channels sequentially and in parallel. So the right notion, the right mathematical notion is something called a monoidal category. So there's another special channel which allows you to swap, so that gives you a symmetry. So this is why, well, tomorrow, I mean, the best way to understand these things is via diagrams, is via pictures. So we are going to have this diagrammatic calculus tomorrow. It's going to let us reason about channels. Any other questions? Okay, in that case, thank you.
Gracias a la audiencia también y nos vemos a las 2 para continuar con la charla de Marcos Carbonio. Y después hay un refrigerio y vamos a otra parte interesante que es los estudiantes van a presentar algunos trabajos, lo que están haciendo con redes sociales. Muchas gracias.
Qué bueno, ¿por qué no? Hola, hola. Sí, este sí da, pero este no, maldito. Razón, pero ya no puedo reiniciarlo.
Porque está en inglés.
Ujú.
Let me just start by saying that it's a pleasure to be here. So thanks to Frank for organizing this and Javeriana. Yeah, my name is Marco, and the idea is to tell you a little bit about session types. I don't know if you heard about this, but I said the topic is, yeah, maybe eventually we'll do some probability stuff. It could be benefit from the stuff that Pavel was talking this morning. But here it's like I will talk about standard concurrent programming. And the idea is to use types, particularly session types, for guaranteeing some correctness properties that you want to have, you would like to have when you do concurrent programming. Okay, I made this map. I don't know why, but I've seen people doing it, and I think it's fun to see where people have been. So I'm from southern Italy, so that's where I grew up. So one of the most remote parts of Italy, and I've been basically, these are the main places where I've been working. So in Pisa, where I did my undergrads, then I did my PhD in Denmark. That's where I actually met Frank for the first time. And then I was in London for my postdoc, and then I've been since 2010, I've been at ITU University Copenhagen in Denmark. So what is it that I want to talk about? I divided, so there are 4 slots of 45 minutes. So roughly, I will try to fit each part in a 45-minute slot. And so the first part, I will just to define some programming language. I call it Toy Erlang because I want to, probably you've heard about Erlang, the Erlang programming language. So I made a very simplified version of that, and I will just go through its syntax with some examples. I will define its semantics, which is really, I don't know if you've ever heard about semantics, but really it's a more precise way of defining how these programs are going to be executed. And then in the second part today, I will forget about Erlang, and I will introduce basically session types, which are a protocol language. So I will define a language for defining communication protocols in a concurrent system. And I will tell you a little bit about their theory and what the kind of things that you can do. And then tomorrow morning, the idea is to connect point 1 and point 2 and basically use this protocol language for making specification about these Erlang programs. And the final goal is to make sure that your program, if it's verified, as I will show you in part 3, to make sure that these programs, they follow the protocols that you are given in terms of this language. And then in the last part, I will, so this is kind of, I try to be as basic as possible, just to give you the intuition and how the basic concepts work. And after that, I will try to tell you in the last hour tomorrow, the kind of things that we are working on right now, and what kind of interesting projects could be done around session types and these kind of things. Yeah, just some thanks. So this is most of the work I will talk about here is based on collaborations with my PhD student David and my colleague Jesper, and then these people here, Emil, Alessandro, Ruggero, and Marino from University of Udine, where we are actually working on session types for Erlang. And yes, then I have to thank this one. So the Independent Research Fund and Marco is also partially supporting my visit here. All right. This is the guys who make Beep, but they didn't support me with Beep. Right. So let's go to part 1. Right. So let me just draw some lines. So here we want to talk about distributed systems. So how do we program them? And of course, the idea is to program them correctly. So there is concurrency, which means you have several programs running simultaneously, concurrently. And usually, maybe it's more, but I like to think of these concurrent systems. They have two different approaches. The other based on message passing or shared memory. So shared memory means that you have some memory somewhere and you have many programs that concurrently access the same memory. Okay? So that's one setting. The other setting, which is the one I want to use here, is message passing. So there is not a shared memory, but basically entities, programs in your concurrent distributed systems, they interact by exchanging messages. So they send messages to each other somehow. And just let me say that these two approaches, if you want, they are also equivalent. You can actually represent shared memory in a message passing systems. For example, you can just make a program that is the memory, and everyone else writes to this memory, to this program. And vice versa, of course, you can reserve some parts of the memory where all the programs can write, and there are specific parts of the memory that are meant to be something like channels between programs. So just to say that the two approaches are somehow, you can encode one into the other. But basically, I mean, the focus is, we will focus on languages for communication-based systems. And the question is, really, how can we make sure that such systems are, we can produce correct concurrent systems. And really, so the question is, what are the good programming disciplines? How should we program? What are the approaches that we need to use for producing correct software? Right. And also here it boils down to the question, what does correct mean? Correct could mean anything. So what are the notions of correctness? When I say that my system, my program, and that applies not only to this concurrent system, but to any kind of software, but doesn't mean that my software is correct. And in concurrency here, I just have 3 examples. You may have different levels of correctness. First, the first one here I said correct communications, and this will become clear a bit later what I mean by that, but I really mean how do we make sure that these programs communicating with each other, that they actually communicate correctly in the sense like, if I'm sending you a message, are you actually going to read it? Are you expecting to read the message that I'm sending? And vice versa, if I'm expecting to receive a message, is someone going to send it to me? Then you can have more complicated properties or notions of correctness, like deadlock freedom. I guess, have you ever heard about deadlock freedom? So the idea of deadlock freedom is that it's a property that avoids deadlocks. And what is a deadlock is that your system, while executing, at some point it gets stuck. It could be, a typical example is that we are just 2 people, me and Pavel, and I'm expecting a message from Pavel, and Pavel is expecting a message from me, and I'm going to send the message to Pavel only after I receive the message from him. And he's doing the same. So then we're stuck. That's a typical example of deadlock. So how can we guarantee this kind of properties? This is a harder property to guarantee. And then you can have other applications. Here I just made security application because in one of our projects, actually, we are interested in these kind of things. And here you have more complex properties that in order to guarantee them, you need more complex techniques. And here I'm trying to make this point because I want to place session types at the very top level here, the easy things that all programs should guarantee. Right, and that leads me to the Gainer project, which is one of the things that has motivated this introduction to session types by using Erlang as well. So the idea of this project is that, so the Gainer thing stands for Gradual Session Types for Privacy. And the idea is to introduce session types for the Erlang programming language, which Erlang, I will tell you in a minute what are the features of Erlang, but Erlang is not a typed language. And then the idea is to use session types for reasoning about information flow. So you have one of these distributed systems with many programs, entities running in parallel, and you're interested in knowing how information flows from one program to the other. And this, from a security point of view, is important because you may have some nodes in your network that are trustworthy and others that are not. And you would like to make sure, you're usually interested in guaranteeing that certain information, certain data, is never transmitted in some not trustworthy locations. And here we have this was actually where I just got some money from these guys here. They're not participating to the project. Let me say that, otherwise they get upset. But they gave us some money to do some research on this. And the nice application that we are thinking of is WhatsApp. I mentioned WhatsApp because the money came from them, but it's any messaging app. And one example that we've been using is this one in the war in Ukraine. We were discussing this yesterday, actually. So what happens is that it turns out that soldiers in the front in Ukraine, they are communicating with each other and with their families. And in order to do that, they use either Signal. Do you know Signal? It's another messaging app, that's actually nicer because it's open source. Or they're also using WhatsApp. And what happens is that, we know on WhatsApp, they always advertise this end-to-end encryption, right? And so we are kind of sure that whatever we write in our message, the message is encrypted at your phone and can only be opened when it's delivered on the other, at the receiver side. So WhatsApp is not able to see what's inside the message. And the message usually goes to WhatsApp servers, and then the servers, they will pass it around, and eventually it will be delivered to the receiver side. But it's always a black box, and you have no idea what's inside. So that's safe. However, for WhatsApp to deliver the message, to take it from me and deliver it to the destination, has to have some information, right? One of them usually is also your ID, which usually is your phone number with WhatsApp. But there is also other information. This kind of information is called metadata, and it's not part of the message of your hello, how are you to your friend that is encrypted. That one you cannot see, but there is some extra data that goes together with a message. And this information could be, sometimes has, from that you could actually kind of guess also the location or where the people are sending the message. And talking to them, it seems they say, oh, well, this information, we cannot disclose it by law, we have to destroy it as soon as it's used, and blah, 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 blah. However, you don't know where these servers are. So usually it's a replicated system. They use, I think the WhatsApp servers are implemented in Erlang, and they use some sort of distributed consensus algorithm. Like, I think they use Raft, actually. If you know that, but it doesn't matter. But what happens is that these servers are replicated, and they are located at different places. And maybe if they are located in not safe areas, places where there are not good regulations, then this information could be leaked. But anyway, so let's go back to Erlang now. Are we doing the time? Yeah. So does anyone know Erlang here? You're programmed in Erlang?
Oh.
You just know it, okay. So I've never programmed seriously in Erlang. But it's an interesting language. It's a functional programming language. Pavel this morning was mentioning there was someone knowing Scala, if I remember correctly this morning. I was saying that, of course. I'm sorry. I didn't remember who said that. Sorry. It is a kind of, I mean, it's not a very pure functional programming language. There is a lot there is a little of imperative things. So you can do sequencing, although the way it's compiled and it's actually implemented in a real functional programming language. But it's been developed by Ericsson in the 90s. It was used only for telecommunication, but the great thing about Erlang is that it's fast and it's really easy to use, and it's focusing on communication. So it's not. I mean, you have send and receives. They are built in, they are native in the language. It's based on the actor model. I will tell you a little bit more about this, but the idea is that you have these actors. They're called actors. They are entities in the system, and what they do, they just deliver messages to each other's mailboxes. So each actor has a mailbox, and then everyone can write into this mailbox. It's not really used a lot anymore. I think it's been replaced by Golang and I think Elixir as well, because so Elixir is really Erlang. Actually, Erlang and Elixir, they are compiled to the same thing that is called core Erlang, or well, for some compilers. But I don't know. But Elixir, I don't really like it. It's a little bit too verbose for me. But yes, Elixir is another version. But the point is that something like WhatsApp, their servers are written in Erlang, and they're not going to change that. It's too expensive to switch to recode everything. So that means that actually I've heard from them that they still are interested in pushing and supporting the language. So maybe in a few years we will see some new version of Erlang that will freshen up. Yeah, of course, Ericsson, I guess they're still using it. But yes, so we thought that we wanted to, we eventually were interested in doing this non-interference stuff for these messaging apps. So we've been trying to develop a session type system for Erlang. So I'll really use it. We use it here. So I was talking about the actor model. So here I have a nice picture about how it works. And then you see many actors, and each actor has a mailbox. So a mailbox is nothing but a queue. Okay? So other actors can write in your mailbox, but you are the only one who can read from it. Okay? It's very simple and it's very natural. So everyone can put messages into the black mailbox, but then the black actor can read from it, and that's it. So it's kind of a little bit more restrictive to standard concurrent systems, but it's quite nice for session types actually. Here I have the syntax. So I've made a very simplified version. So now, maybe you've never seen this. I'll try to go through it quickly, but it's not very complex. So there is one part, which is the functional part. And here you have, so basically what you have in Erlang is expressions. So each program, each actor has an expression and has to evaluate. And an expression can either be just a standard variable, it can be some constant. I will give you an example in a minute. A constant, like a number or a value, it doesn't matter. Then you have this operation here, which maybe is the most complicated one, but it's basically some sort of lambda abstraction. So if you can also have that in Python, I guess. You can have lambdas, right? Are they called lambda in Python? Yes. So you know what they are, right? And then you have function application. So I can define some, this one has the extra feature that is recursive. So you can basically use F inside E to do some recursion, okay? In Erlang, actually, you don't have this. In Erlang, you can define functions separately, and then you can use them. But I wanted to keep the syntax very simple and compact, so I just defined it like this. You have function application. This is sequencing. This is part of Erlang. So that means first evaluate E1, and then evaluate E2. If then else, standard. And then there is this communication part. There are also expressions that need to be evaluated. And basically they are, in Erlang, in real Erlang, you only have send and receive, okay? But they are much more complex and you can do lots of things. Here, just to keep things simple, and I divided them into two types of sends and two types of receives. So the first pair, which is send and receive, is just I'm sending to some actor P. I'm sending some expression, the value of an expression E. So that means evaluate expression E, you get some result, and then communicate it to P. The self is not very important here. In Erlang, you would have to use it. And then you have the receive, and here you do some sort of pattern matching. It means receive from some actor P. So go in your mailbox and find a message from P. See what the content of the message is, and substitute and use it in E. Okay? And here is the same, but instead of receiving some message, I have just pure pattern matching. So I have some labels, and I use this for branching because I want someone to send me a message and tell me which branch I have to take. Yeah.
Why do you even need the message? I mean, can that be a special case of the label?
Yeah.
Because the label is the L is constant.
So the X is a variable. So that means it binds in E. L is a constant. And actually here I'm even more strict. I'm assuming the L's are some special constant that later you'll see I'm going to use them in the types as well. So in Erlang, if you write it in Erlang, then you will have to make assumptions. You have only one type of thing where you can have these are called patterns in Erlang, and they can be much more complex. But here I kind of made a strong restriction, and I'm saying, well, you either have, you have a singleton here, and it has to pattern match something of this structure, or you can have more, but then they all have to be constants of this kind. So I'm just making it more restrictive. But yes, otherwise this could be, I could have written just one thing here and then make it more general. So it's just that I didn't want just because for me it's important to have it separate like this, because then we will have different types for this kind and this kind. So here's an example. It's just a customer. And what are the ingredients that I'm using here? I'm kind of using everything from the language, I think. So what is this customer doing? It does something repetitively. So that's why I have this let rec f of x. So basically it's like a declaration of a function. I'm applying it to 5 as a starting point. And then I execute this code. And every time there is a call to the function with a new value, I just go back. Okay? So this is simple recursion. And what is the body of the function? Well, it first sends a message to the shop, so it's a customer. And what it does, it selects, uses, so if it's in italic, it's a label. Okay? So it uses the label price, which means I want to use this method here, tells the shop. I need to get the price for some stock. And then what it does, it waits, it checks on its queue, on its mailbox, and it looks for a message from the shop, and it reads this Y here, which is basically the price that it has received from the shop. And then it checks if this Y is less than this X, which would be its upper bound, say. Then it just says to the shop, I want to buy. And then it sends to the shop its credit card details. So this is again a label, and this is a value, constant. And then it starts again, actually, but after the purchase, but then it lowers its upper bound. So it tries to buy again at a lower price. So this is a non-terminating thing. Just otherwise, if it's not good enough, the price, then it raises its upper bound. Eventually, it will buy. Okay? I mean, maybe it's a stupid customer. I don't know, but just to show how what you can write in the language. Yeah.
Wait.
So why can't you send a label and a value together instead of sending two messages?
You can, and in Erlang you can, not in the syntax that I showed you. Now, in the general setting, actually, we are trying to, what we are doing is we're actually taking real Erlang, not a simple thing that I just made for this. And in there, you have a much general way of writing this. I think it's connected to what Pavel was asking before. However, then the typing check, if you do that, is much more complex. And we would have spent many more hours to actually look into the details. And while like this, I'm telling you, there are two types of sends that you can do. Either you select a branch, basically, or you send the value. Well, of course, in practice, you can put them together and make maybe just a tuple here and there with both sides. Absolutely. All right. Semantics. Did you study semantics of programming languages? Anyway, the idea of semantics is that you have the syntax of the language, and then you want to give a formal way. In a formal way, you want to tell me what it means for a program to be executed. Okay? So in practice, what you do is that you just write your program, you give it to the compiler or the interpreter, and then this is being executed, right? And what you hope is that the way it's executed is what the manual tells you, right? But usually in formal methods, when you want to reason precisely about programs, what you do is that you give a more precise mathematical definition of what it means to execute the program. And what I'm going to do now is I'm going to do this for this language here. It's not very different, okay? So first of all, I'm going to talk about configurations. So I'm trying to represent all these actors running in parallel, okay? And so I have many actors, P1 to Pn. Each of them has an expression in the language that I showed you before. And each of them has a mailbox. So this is the mailbox, and it's a queue, basically. Okay? And then what I want to show is that while I start executing one of these expressions, I want to show you how the whole system evolves in very small steps. So how do you do that? So this is basically the semantics of recursion. of the let rec. So if somewhere I have an actor that has an expression of this kind, so it has a recursive definition of a function, and it applies to some value v, then what you do is, I should point to that. What you do is that you take the e here of the let rec, and you basically replace the whole thing wherever you find f in e. I will show you an example of this. And also, you will substitute the variable x with the value v that you are applying the function to. And then you continue. So here is an example. Here I have a logger. It's basically a actor that recursively receives a message from the shop and then discards it. So you can see here, I have g of z. I receive something, x, I discard it. Maybe in real implementation, we would save it somewhere. And then I start again, and I evaluate g of z again. Okay? So this is just a recursive definition of a function. And if I apply that definition there, what happens is that the logger, so I have to take the expression e up there, which is basically this whole receive here, and I have it here. And then I replace g with the whole thing itself, and I've done it here. And then unit will replace will replace z, and I get it here. Okay? Let's look at something a little bit more interesting. Sequencing, this is very simple. So if eventually I evaluate an expression, so if I have two expressions in sequencing, in a sequence, and I have a value, then I can discard that value and continue evaluating. That's kind of simple. If then else, if I have some actor and I have an if then else, and the guard of the if then else is true, yeah, then it means that I can change this and reduce it to E1. Okay? If it's false, well, you have to continue evaluating E2. Now let's go to concurrency, which is more interesting. So assume I have some actor P who is trying to receive a message from Q, message X, and then continue as E. And in its mailbox, we can find a message from Q called V. Okay? So P wants to do a receive from Q, and in the mailbox, there is a message from Q. So what do? So how does it change? Well, we continue evaluating E, where we replace X in E with the value V that we have read from the mailbox. And now this thing has disappeared. So here there is a side condition that says that Q is not in this part of the mailbox. This is because when we want to receive from Q, we need to go and find the first message in the mailbox that was sent from Q. So basically, we kind of preserve the order in which the messages from Q were sent to P. For example, here, if I have the logger that had done the unfolding, basically, of the let rec, now it has to do a receive from the shop, and there is some message, some log from the shop in the mailbox. But before there is some other message from some other actor R, then yes, we can read it and move. So we reduce this receive and move to this new term here, new program expression. The send is kind of opposite. So assume that you have an actor P who wants to send a message to Q, a message of some value V. Then what it does, it just goes to the Q's mailbox and it drops the message there. So here you can see that after I execute the send, I put the message PV into the Q mailbox to mean that the message was from P and V is the value that I wanted to send. Yeah. This is a queue, so remember that the message, you always put it at the end of the queue. You always read from the top and you write from the end. And the labels, we'll skip this, they are very similar. So the output, just put the labels instead of the value that we wanted to put. And when you do a receive, you will find, if you find one of these options, then you read it and you continue with that branch. This is like a case. So the question here is, what happens if there is a message, but is not one of these labels here that I have? Sorry? Yeah, basically it's stuck. And this is like one of those basic errors that you would like to avoid. And it's really easy when you write, not when you write my customer example, but if you write a big program, it's really easy to get into these very small errors. I kind of cheated you a bit with the semantics. All the cases I gave you, for instance, the send, I was assuming that here the value you're sending is a value. But if you remember from the syntax, here I could have an expression. So what do you do when you have an expression here? Because the semantics is telling you can send something only when it's a value. So if you have an expression, first you need to evaluate it and see what its value is. So for instance, if I have 5 plus 2, I cannot send 5 plus 2. I need to first compute what 5 plus 2 is, and then I can send the 7. So I should rewrite the rules a little bit differently. And what you do is usually you define this notion of context. And basically the context is it's basically the syntax of the language, but the C points out where you have to evaluate first. So for example, if I have an if then else, before evaluating E1 or E2, you need to find out what the guard is. So this one is saying, oh, if you have a if then else, please first evaluate the guard. Then once the guard becomes a value, so a true or false, then you choose which branch you take, and then you start evaluating the branch you take. Of course, here you could get 5 or a string, and then again, either you get stuck, or in some languages like C, for example, if it's different from 0, it assumes it's true or false. True. But so, and again, what does that mean? It's not very precise. And again, here it's like in untyped languages like Erlang or Python, since you're all using Python, you can make these mistakes very, very easily. And this has nothing to do with concurrency here. Here it's just lack of types completely. Again, if you have a send, you first need to evaluate this thing here, and then you can continue. And then you can rewrite the rules like this. I'm not going to go through all the rules, but basically now it says, okay, when you have to evaluate something, this can be inside some more complex expression. and then you can evaluate it inside. Right. How about the shop? I've told you about the customer, I've told you about the logger. What was this? We were both talking to a shop, and here is what the shop does. It's again a recursive behavior. And here the important thing that I want you to see about the shop is that it offers options. Okay, it uses these labels to offer options. Options are like methods, if you want, in a object-oriented setting. So the customer can always choose one of these options. He can either choose to put a price, or to go and buy the stock, or he could choose also this reset option. And this program we wrote here, at some point it does the buy, so it chooses this branching. Some other point it asks for the price, but it never chooses the reset branch. And this is fun, okay? It's safe. However, if the customer chose like the hello branch, but the hello branch is not here, that would be a problem around Ruby and So here again, the question is, how can we make sure that these things are compatible and fit together, and they never get stuck because we forgot to include that particular branch?
Does it include people? If it's not any of those?
You can do that in Erlang, I think, but not in this language. Yeah, you can also do that. That could be, but then what do you do in the default? Is it programmed correctly again? I don't know. I mean, then it goes also to other things like exceptions and this kind of stuff. But I will not get to that. There is research on this, there are papers on that, but that's a bit more complex. But yeah, but it's a very good question. Right, what happens if the customer asks for a price? Well, first it logs the price to the logger. It sends a message to the logger, and then it sends the price to the customer. If the customer asks to buy, then first it receives this Y here, which is the credit card. Then it logs with the credit card, and then it starts again. And this one, the reset, does nothing. It does nothing. It's an extra branch that is never used by the customer in this example. And I think here the important thing is that you see the logger is involved in all branches, and it's always waiting to receive some log from the shop.
If the shop will change the price.
Yes, I'm assuming that this read price thing is something that is even that actually read the price from whatever, something else. So the price is updated at every loop. Yeah. So you start with a read price, but then every time you loop, you read again. I mean, okay, maybe it's not most realistic way, but it's just it highlights the features of the language. Right. Is it okay, friends? If I just use 5 more minutes?
Yeah, sure.
So things can go wrong. I've already showed you many times how things could go wrong. The label was not available, or the pattern matching didn't work. So here I could actually say, imagine that you could just do things wrong. You could just swap this operation, and then you get stuck. Okay. And again, here I'm pointing this out because this is a very basic property that you would like to avoid in your program. And here I'm not talking about very complicated properties like, oh, how can we how can we guarantee that there's never a null pointer exception, right? Or that we actually compute exactly this function, or we never deadlock, right? Deadlock is also, I mean, this is a very basic thing. I mean, you're swapping the things while programming, and then your program will go wrong for something kind of silly that you could have prevented it somehow. I will stop now, and we take 15 minutes break, and then I'll start again from here.
Okay.
control the case. So before you start with the second part, some people have been asking some questions. Like one question was about evaluation, if it's a lazy evaluation or eager evaluation. That means when you compute the expression before setting it, or for example, that's one question. The other question, Anna was asking, you want to ask her or you want me to translate for you? Okay, so she was asking about this example with the customer and the shop. If one talks to the other and then the other they talk to each other, could they run indefinitely in that particular way you wrote the program? So,
All right, so two questions. Is it okay if I go with the first one?
Yeah,
and,
sure.
And then I'll answer the one about exam. So about the evaluation order, we're actually discussing just during the break offline. So it is not lazy, okay? So if you look, this is basically function application. So I have a function, this is basically a function. And here is a value I'm applying it to. So this rule is telling me that I can execute the application only if the right thing is a value, okay? So that means that if it's not a value, first I need to evaluate it. And this one you can also see here in the application definition, that the context is always on the right. So, and I can evaluate the left side of the function application only once I have fully evaluated the right one. Now, it's not, okay, of course, lazy and like in Haskell, for example, and eager, they're not always equivalent. But here it's even more important because these operations here, the send and receives, they are like side effects. And because of that, actually, in a functional language, it shouldn't really matter in which order you evaluate things. Oh, it has to some extent. Haskell teaches us that, for example. But here, if I have something like this, so let me just go back to the real syntax here. If I have something like this, and the order in which I evaluate these two expressions here is really important in terms of side effects, because I could have send and receives here and send and receives here. And if I don't care, if the order in which I evaluate these two guys is random, it means that randomly I could either do a send or I could do a receive that I have here, for example. So it's really important that there is a deterministic way of evaluating it. The choice of doing right first or early is not very important for this, but it has to be fixed. So here I've chosen to do it like this. But however, for the send, you cannot send code. You need to send a value. So you need to evaluate. You have to have something that, and also has to be a closed term, which means that it shouldn't be variables free hanging around there. About the other question, yes. Actually, there is more into this. So the question was whether this thing loops forever. Yes, it does, because you can see that every exit point, you just, no, sorry, not here, but here and here, you just recursively call the thing. So, and you can say the same for this and for this. Yeah, I've chosen to do that. Actually, there is more. I've chosen to do that because I'm simplifying the theory of types. And later, tomorrow, I will show you that this is well typed. And it will have a protocol that describes how these guys are to interact. And I need it to be like this because of the simplified version I have. That's why it's, but yes, to start with, I have thought of an example where actually after you bought, you stopped. Well, the server would keep restart again, but the customer would just stop. But yeah. Okay. All right. So is that all? Yeah. Right. So let me just. I left this slide also during the break. Maybe you've read it already. So I have a colleague. He's an expert in software verification. He actually works with Coq theorem prover, which is a tool for formally writing logical mathematical proofs. And he doesn't work with types. He works with he writes proofs about properties of systems. So what he does, he writes maybe a language like the one I showed you with the semantics, and then he builds proofs or a system for writing proofs about a property that you have to give it also to him. Right? So that's much more general. So then you can say, well, I have my program that computes something, and I want to make sure that this happens, and this is a function of this, and it's computed, this algorithm will compute this particular function, whatever, it doesn't matter. So it can be any kind of property. Okay? So, and we always have kind of arguments when we talk about types, because you always say, no, but types are very limited. You can only prove very simple things about types. And this is true, but my counter argument is that types are used by any programmer that uses a type programming language, let's say any Java programmer, while there are very few people in the world who can write a proof in the Coq proof system and prove some very general property. So the idea of types, now why am I saying this? I'm saying this because types are, yes, they guarantee properties, they help for, they provide some notion of correctness, but they are basic concepts. They guarantee some basic properties. So a type system, it gives you very basic ingredients that you want your basic properties that you want your programs, all your programs to have. Typical example is, I guess everyone here has been programming at some point, right? Have you ever used all Java, for example? Maybe Java is the most common. No, you don't like Java. Oh, you use it? Yes. Okay. Oh, sorry. I don't like Java. It's too cumbersome, but it's strongly typed. Okay. It's very verbose. Yeah. Haskell is much nicer, and it's also strongly typed if you have used it. But the point is that in Java, for example, or anyway, any type language, imperative language, for example, if you say that x, you declare x variable, and you say it's an integer, that's a very basic thing. Everyone can do it. Everyone can understand it. And you know for sure that if your program compiles, okay, you can also do casting and weird stuff in Java, but let's forget about that. But you know that it will never happen that you will try to assign a bool or a string to x, because x is an integer. And the type system statically will guarantee you that this will never happen at runtime. Now, At the same time, they provide also an abstraction of the data. And now, but of course, there is also a counter thing to types. This is usually people who hate Java, for example. I don't like Java because it's verbose, not because it's typed. But people, for instance, Erlang itself or Python, God, I mean, can you imagine that there are like how many people now with the hype of AI are using Python, and they write programs and they are not typed at all, and you can write really crazy stuff, and if you really don't know what you're doing, it's really, really dangerous. The kind of programs they can break very easily, and for me, it's like strongly typed programs or languages are for everyone. Non-typed ones, like Python, should be only for artists who really, really know what to do. However, yes.
So how about these languages where you don't declare the types, but they can infer the type of the functions, polymorphic and stuff like that?
Yeah, like Haskell, for example. I mean, yes, that's good. That's maybe the best compromise. However, I don't know, I try to code. Actually, I've been coding quite a lot in Haskell, and my conclusion is that it won't work if I don't start actually declaring the type of functions, because then it makes me think structurally and I really understand what I'm doing. And that's what's I don't know Python well. I mean, I've seen some, but I never really used it. But when I see people writing in Python, especially more complex algorithms, I always get scared. What happens if you are working with a list and then the type of this list is not exactly what you're thinking it is, because you made a mistake in your map or in your filter or whatever. And Python will process that anyway, will let you do whatever you want. And it's great also, it's very elegant on certain things Python, but the lack of types really, really, really scares me. But strongly typed languages like Haskell, where you don't have, but they have a really strong inference system, then yes, that's great as well, but it doesn't work on everything. Sometimes you need to help it in a still. You cannot infer everything. Usually inference I think is undecided. Right. Well, of course it's harder, right, when we have types, because sometimes they're really annoying. And tomorrow I will try to show you an example where by using session types, you can write much nicer things without using types. And then the question is, what can we do that? What can we do that? All right, but and then the question here is, okay, can we use types for communication? So have something simple, basic, that can guarantee very basic properties of communication. And to do that, I'm going to show you the session types, multi-party session types actually, methodology, where you have some distributed code, and then you specify some protocols, and then what you do is these protocols are like types, or they generate types that then you can use to verify the code. This will come out clearer later. But now I will move to my other thing. So the part 2, and probably we will get this finished tomorrow, but that's fine. So what I'm going to show you is a protocol language. So the idea is that we've seen the shopper, customer, logger example, and that was coded in that toy airline language. And now the question is, actually, yes, they are running a protocol, and we actually, after looking at it, we all know what's going on when we execute this whole system. And the question is, can I have a language, have a way of specifying what kind of protocol they are actually running? What are the sequences of interactions that they are going to have when I execute the protocol? Right, and this comes to a very exotic name, which is the notion of choreography. So what is a choreography? Maybe I should read it. So it's a description of the interaction patterns, so the protocols, that concurrent processes must follow during execution. Has anyone ever heard about what a choreography is? Have you one? Yeah. Yeah, you work with this. So, so basically, choreography is a sort of Alice Bob notation. So, if any of you has ever taken a course on security, or maybe you have heard about the Eden protocol, which is broken. And the way they write it like this. They say you have two parties, A and Bob, and A sends a message to Bob, which is this thing here. Then Bob sends a message to A, and finally A sends a message to Bob. So this is a sequence of interactions, right? And each interaction contains a message. Here it's cryptography, okay? So here I have a nonce, the name of A, and it's encrypted with B's public key. It doesn't matter. That's not the goal of this course to teach you about security or security protocols. But this concept of choreography is heavily used actually in security protocols. So let's go to the shop example we saw before. And here I'm telling you, well, the protocol that code in Erlang is running is this one. So what does it say? Well, this is just a marker. It's still recursion. Right? The idea is like a point in the code that at some point you want to go back to. Okay? So just to repetitive. And what happens, the protocol works like this. Well, the customer is going to select one of these options, either choose price, buy, or reset. And in the first branch, the shop will send along the logger a string, the log. And then after that, the shop will send the customer a price. So it's an integer. So here also notice that I'm doing an abstraction. I'm not talking about the exact data, but I'm giving an abstract description of what the protocol is. So I'm saying you're sending an integer, I'm not sending it exactly what. And then you start again. If you select buy, then the customer will send its credit card. So this assume that there's a credit card type. Could be some complex record or something. And the shop will log a string. Already here I'm losing also information. If you remember, the log was containing information about the credit card. And this information here, this level of abstraction in the protocol, the choreography, is lost. And here is the last branch where the shop just logs. Okay? And now here you can have one question I would immediately ask is, oh, but wait, that fits your shop code, but if I have to think about the way you wrote the customer, it's not true that the customer chooses this branch. And again, here is we need to distinguish between specification and actual implementation. Because here, I'm just saying that there is this possibility. I'm not saying that the implementation will have to have it. Right. What's the advantage of having these choreographies? Well, first of all, you lose this locality concept. When I described you the system before, I had to tell you the code for the customer first, then the logger, and then the shop. And then by looking at it and hopefully understanding it, you kind of drew in your mind, okay, yeah, they match. If I execute them, they will follow that choreographic protocol. But here the protocol, there's no local thing. It's a global description of what the system is going to do. Yeah, so basically, there are many advantages. One is it gives you a global viewpoint of the entire system, but also it can be used as a blueprint of the entire system. So you could actually, as a software architect, you could say, well, the implementation has to respect this protocol. It's easy to say. And then one extra thing that you get for free. So this is a property actually you get, at least in this system that I'm showing you, is that if your code is following the protocol specifications, and the type system will verify until tomorrow, then you get deadlock freedom automatically. Why? Because I'm not talking about actions, input-output actions, but a choreography by the customer that is precisely reset by the shop, which is one of these choices. Then this, and starting. And something like this currently is in deadlock free. Okay, this is maybe the informal way of saying this. I can also show you format. Yeah, and then this is actually this idea of choreography started in the early 2000s. Actually, when I moved to London, I joined this WSCDL working group, which was supported by W3C, the Worldwide Web Consortium. And the idea there, they were trying to develop choreographic languages for web services. And that's how all this thing about session types and multi-party linked sparked. And one of their key sentences was about choreography was dancers dance following a global scenario without a single point of control. And this was in contraposition to the orchestration, the concept of orchestration that you had back then in web services, where you had an orchestrator that would communicate with different services and coordinate. While here at choreographic level, you don't have a single point. Everything is like global viewpoint. Of course, being deadlock freedom, it means that there are programs that you cannot, or protocols that you cannot model. There are ones that are not deadlocked. And sometimes there are interesting deadlocked programs. And of course, choreographies then do not capture all the possible deadlock-free programs. Just a disclaimer saying that we are modeling some subset of all the possible interesting programs. And interesting. Just one more thing. I will use these three words equivalently. So I will try to use the word choreography, but I may say global type because they use as types. Global description maybe sometimes just so that you don't get confused. So we saw the example. Let's look a little bit more in detail. So basically these choreographies are like really a language for describing these protocols. And there are three basic ingredients for building a choreography. One is the core thing of a choreography, which is the interaction. So an interaction is really when I write a choreography, I say there should be a message from A to B. And a rhythm that is. So here is an example. I could write something like this, which means the shop sends a string to the logger. So this is the core, the basic block of a choreography. Then you have branching. So branching is also a sort of interaction, but it's not about transmitting some data of some type, but it's about choosing one possible path in the protocol. And here, for example, the customer chooses one branch, could be either this, or this. And I can have many more branches as well. And then the last thing, you have recursion. We have seen it before. And really, it's a go-to so that you can express repetitive behavior. And if you combine all these things, you can write interesting protocols. This is the syntax of the choreographic language. So the first one is the interaction that I showed you. U is some type. At least in this version, has to be some basic type, like a bool, an int, or a real, or a string, or whatever. Then you have branching. So this really means I'm using here this kind of set notation. So I have many possible labels, right, indexed by some index set, and each of them has a continuation. And then this is recursion. This is termination of the protocol.
Mark, is there any reason why they chose tail recursion, like T can only appear at the end?
Yeah, this is a good question, actually. Right, so again, you want this language to be as simple as possible. And what you get is that actually to improve, so the programs that I can write here with tail recursion are finite state automata. So that means that also this language here, formally the syntax, is a regular language. And also you generate a finite state automaton, so you can also recycle lots of properties from finite state automaton. And actually there is some work that shows that there is a one-to-one correspondence, if you want, between these types and communicating automata. So that makes things actually easier. In many, for instance, you can compute reachability, and also given a global type with recursion, if you have unfolding in it, you always have a finite number of terms which you can generate. So that's really easy for. And the idea you want is to have a language that types, a protocol language that types something like the Erlang thing, and but still that allows you to prove some properties that then that can be reflected down to the programming language. I will mention a few things about macro chains maybe tomorrow if I have time. About an advantage actually of having this tail recursion. So now I've told you, yeah, I have this language. What can I do with it? In the beginning, I told you, yeah, okay, I can write these protocols. It's nice, and I would like my program in Erlang to somehow. I want to have an automatic way of verifying that, given a protocol here in this choreographic language, I want to check whether my Erlang code respects this protocol. And here I have these global things that describe the protocol, but Erlang is still going to be a set of programs running in the environment. Now the question is, okay, how do I draw the line? How do I connect something like this to something that is distributed for real? Because in the end, you want to have, I mean, this is not concurrency, right? This is a protocol description, but eventually you want to have, if you have n actors, you want to have n programs that you can deploy concurrently and execute. So eventually you need to go from global to this local description for each actor. And so how do you do that? And what you do, you use something intermediate. It's called local types. And local types basically are, given a global protocol, the idea is that can I talk about the behavior in the global protocol about the behavior of a single actor. And what you do, so the idea is that you have these global protocols, like these choreographies, and what you do is that you use this function here, it's called projection, I will tell you in a minute, to generate a local abstraction of the code. So, for example, this is the syntax of these local types, and they look like a bit mixture between the send and receives from Erlang Rousseau and the choreographic thing, because you have type abstractions here, you don't have concrete data, but you don't have any more interactions. If you remember in the choreography, I write A to B, but now I write input and outputs. So for instance, this one is saying send something of type U to P, and then continuous T, receive, select a branch, offer some branches, and then recursion like the others. So for example, if we look at the customer, its local type is something like this. It makes a choice. So the O plus here means decide. For those of you who know it, it's called internal choice. So it decides which branch it wants to select, communicate that to the shop, and then if it selects this, it waits for a message from the shop. If it selects this, it sends its card. Here it does not, just start again. Because if you remember, the reset branch is the shop who does something only with the log. And the question is, okay, if I give you a choreography, can I automatically generate a local type for each actor? So I give you a choreography, which is a protocol description, and then I tell you, can you automatically generate the behavior, the local type for the shop and the customer and the logger? And the answer, yeah, of course, is yes. So you have this operation called projection. Sometimes it's even called endpoint projection because you generate endpoints from a choreography. And it's a function, basically. It's like a compiler, if you want. You compile a choreography into these local types. And it's defined as follows. So for instance, if I have an interaction, I'm projecting some row P, and I have an interaction from P1 to P2 of some value U, of something of type U, then if I'm projecting P1, then I will produce an output to P2. Because here, for this interaction to happen, it means that P1 has to send a message and P2 has to receive it. On the other hand, if it's P2 receiving, I'm projecting P2, sorry, then I will generate an input because P2 will input from P1. If what I'm projecting is neither of these guys, then I just go on and project G and G. So, for example, here if I'm projecting the logger and I have this choreography here, then okay, what is the logger doing? She's doing an input, right? So yes, I generate an input from who? From the shop of a string, and then end, because this one terminates in this case. Now, yeah, recursion is, it can be problematic. So if you have a mu t here, basically, let's say that you generate end if in the choreography G, P doesn't appear at all. Because it's not involved in the rest of the protocol, so you just do it, it stops. However, if it is involved, then you continue projecting. And there is this side condition here. The problem is that this projection thing is a sort of erasure, so you have to be really, really careful. Let me show you an example. So, for example, if I write this choreography here, I have mu t, and then I have A to B of something, and then I do T. Okay? So this is a protocol where A and B continue writing to each other. But before I do this, assume that I have C writes to A a string. Okay, so first this, and then A continuously send an integer to B. Now the point is that if I'm projecting C, so if I'm projecting A, what you do when you project A, you kind of erase the things that are not interesting. So this is not interesting, this is not interesting, so you know that A incoming arrow is an input, A outcoming is an output. Simple. However, if I'm projecting C, so let's resume this. So if I'm projecting C and I'm erasing the other guys, and then I do the projection here, I'm left with mu TT. And this means nothing. This is a bad program, should be wrong, shouldn't be allowed to be written, because it means nothing. It's not productive. And basically this side condition here, it basically means that the variable t, the recursion variable t, is guarded. Guarded means that for C, C will be doing something before you do t in between, but it doesn't. So in this case, for example, you would project this to end when you're projecting C. Yeah.
Shouldn't that be then approach BG and then G bar? Do you want to check it on the projection, not on the G? Because G might be.
Yes. Yes, but G bar does. I think there is. Yeah, it's missing the P also. So, but yes, you want to check in there. Yeah, because still G could be something interesting, but it's not involving P. Yeah, I don't have the definition of G bar here, but it's yes. Thanks. Right. But now and I think maybe that's how I conclude today, the projection of branching. And branching is a huge problem. It seems easy, it seems trivial, but it's not. Why? So let's assume we have P1 and P2, right? And they have all these branches here, and I have to project. Now, if I have to project P1, or if I have to project P2, no problem. It's very easy, right? So P1 is sending, so I need to use the O plus with all the branches, and then I recursively project. If I'm projecting P2 dually, I do the ampersand here, external choice, offer all these options, no problem. However, if I'm going to project something else that is not these two guys, how do you project it? You have many branches, and in each branch, this P, which is not P1 and it's not P2, may behave differently. And now the question is, how can P know what P1 and P2 chose? So this is a branch between P1 and P2. And at some point, P1 makes a choice. It communicates to P2, but P is a third actor, third guy. How does he know what choice was made? So that means that in general, you could write wrong choreographies whose projection does not exist. For example, I could write the following one. I could write A makes a choice with B, okay? And there are two labels. And in here, for example, I could write C writes to A, or to D even, and here C writes to B. How does C know which branch these two guys decided to choose? And based on the branch they choose, C should either write to D or to B. So two different actions basically. Yes. So that means that you need to be a little bit more restrictive. Now, people have been working on this for years and years. But the original paper on this stuff went for the easiest version. And the easiest version says that basically any other guy has to be projected the same in all branches. So basically, P's behavior in the continuation has to be the same in all branches, which means P doesn't need to know which branch they decided to take because it would behave anyway the same. Now, this is very restrictive. I'm going to stick with this for this lecture, but there are extensions of this. And if you're interested, I'm happy to talk to you maybe offline.
And Marco, in the third condition, you have an equality there. This is syntactic equality, or what kind of equality is that?
Yeah, that's a good question. So in the original paper, it's syntactic equality. You can generalize it to unfolding equality. So if you have these recursive muse, you could say it's equivalent up to unfolding. That one, Popol 2008, which was the first paper about these multi-party session types, theory of multi-party session types. So sorry about that.
This paper is important because Popol is like the number one conference in programming languages. And that paper got the prize of, what's it called, the prize?
Yeah, it was the most influential paper in the last 10 years. I mean, subsequent 10 years.
So it's the most influential paper in the last 10 years in the best conference in programming languages.
Right. So we assume that they are syntactically equal, but you can generalize this and you can make it more flexible, but then the theory becomes much more complex, unfortunately. Here's an example. How do I project? If I have to project customer, then customer is part of the branching, so it's easy. We just do the O plus and then have all the branches as expected. However, if I'm projecting the logger, here you can see that the logger is not part of the branching. So we will have to satisfy this condition. And in this case, we do, because the logger is always receiving a string in all branches. And the nice thing, at least, the flexible thing, is that the logger doesn't have to be the first guy here. It can be in other positions as far as its projection.
What would go wrong if, say, in the Bible, we didn't so the logger would still have his descent type, local type, of getting stuff from shops, but nothing would go wrong.
Right, so this is an interesting question. So in practice, you're right. So if I remove this completely, since I have recursion, the logger is still supposed to be there waiting for a message. If I didn't have recursion, then I could talk about deadlock, because then the logger is there waiting there forever, and that's maybe something you don't want. In the recursive setting, in this kind of recursion thing, then it would be fine. However, from a theoretical point of view, it doesn't work because you have an infinite path where the logger is never executed. In practice, it's fine. Yeah. It's always like this, right? And I think there is now I don't remember which paper it is, but there is a paper where they actually discuss this, and they would allow what Pavel just said to erase this under some fairness assumption, which means that you assume that eventually you will take the branch where the logger will receive the message. All right, it's time. I think I will continue tomorrow. So the idea, I'm just concluding now. So I want to tell you a little bit more about a problem with recursion that we found out recently. So it's some work that my PhD student did. And it's actually quite cool. And I will show it to you tomorrow in the beginning. But otherwise, we'll stop now. Thank you.
Bueno, un refrigerio allí, y como está solamente la mitad, por favor coman 2 refrigerios cada uno, porque hay 80 refrigerios allá esperando. Muchas gracias por venir, lo esperamos mañana cumpliditos. Todos están fotografiados, así que tienen que mostrar 2 cosas, una el viernes.
Yo no trabajo en esto.
Ah, pues este evento no me tocó hoy.
Ah,
No hay más sesiones después de esta que hagan una cuestión.
sí. Tienes razón. Perdón, recuerden que la sección de estudiantes ahora es que todo refrigerio. Es más corta. 15 minutes from now, after the coffee break. Bienvenido, Johan, es nuestro primer speaker y luego sigue Jordan.
Thank you. So hi there, yes. So today we're going to talk about this article we managed to get accepted at the Computational 2024 conference, which is titled Fairness and Consensus in an Asynchronous Opinion Model for Social Networks. I'm Sebastian Betancourt, research assistant under the supervision of Professor Frank, which is also a co-author, and I'm working in the Promueva project. Perhaps some of you guys have heard of it. Basically, it stands for, in Spanish, of course, Computational Models of Social Networks applied to the polarization of Valle del Cauca, which is the region we're in currently. And this work is a result of the research made in Objective 1, which is to develop a computational model of social networks for the study of polarization in social networks. So this is what we're going to talk about, formal models for social networks. More specifically, we took one of the, let's call it canonical models, or one of the most known models, which is the group model, and we proposed a modification of it because we believe it might capture social network phenomena or more current social network phenomena more appropriately. Then we're going to talk about consensus and what that means in a formal context, and what are the conditions necessary for the agents to reach consensus. So that would be strong activity, total freedom, fairness, which is of special interest. We're going to see some notions, some fairness to classify them, and a new notion we believe it's relevant for this use case. Then we augment the model with some dynamic influence, and then we're going to talk about what are we interested in right now. So, Gracias. Thank you. So we started based from the work of the group, which is a model proposed in 1974, where a community, perfect, yes, where a community is a weighted directed graph, just like the one you see over here, and each of the nodes of each of the agents have an opinion value between 0 and 1 in relationship with the degree of agreement with an underlying proposition. So if the proposition is AI poses a threat to humanity, then the red agent completely agrees with a value of 1.0. The notion of synchrony in the sense that at each tick, everyone sort of talks at the same time, everyone sort of updates themselves at the same time, that we believe it may not be the most accurate recipe for modern social networks that we explore right now. We wanted to capture this notion of every node updates or decides when to update. Basically, if you take up your phone, you decide when you read, I don't know, your opinion with someone else, or you decide to talk, And so we decided to modify and propose a new model that includes, there's a button here that turns up this one. I'm not sure which one is it. To include asynchrony by letting only one of the edges or one of the arrows be chosen at each time. So suppose we choose this one over here. So we're gonna influence or update only the yellow agent under the influence of the red one in certain way. And this is the function we're going to apply, which is basically a weighted average or a difference that is based on the difference of opinions. So the result will be much different. The yellow agent updates to 1.85 and the other two remain exactly the same, right? So this evolves very differently from the group model. And one of the main points of interest of the root model is that we can easily compute or see to which consensus value they reach to. And a consensus of opinions is basically to which opinion all the agents converge to. In this model, we define it formally as the convergence of each value of opinions of the agents to a same value, right? So the limit in being infinite. So we have this example over here, which is very basic, and we have the plot that corresponds to each of their beliefs. If we sort of start by choosing edge A, which would be to let agent 1 influence agent 2, and then choose edge B, which would be agent 2 influence agent 1, and then C, and then D, and do that infinitely, to an infinite amount of times, you'll see this sort of behavior, right? Like they reach consensus over a value, let's say close to 0.5. Then this is very interesting in the context of the project we're working on, because we're talking about polarization, and in some sense, consensus is the opposite of polarization, right? If we all consent to a value, then polarization is 0. So we managed to actually identify some conditions, some sufficient conditions for consensus, and we're going to see these two counterexamples. So the first condition is what we call strong connectivity, which is basically that you can like follow a path from any node to any other node. So this is a counterexample. This is not strongly connected because you cannot follow a path from, for example, agent 1 to agent 3, right? You can only reach at most agent 2. And it is easy to see that with this, if agent 1 and agent 3 have different opinions and they never influence each other, they will never reach a consensus. They will never agree on something. Then we have a second condition, which is puppet freedom. And this is basically that the weights of influences are never equal to 1. Because if that happens, then if your influence over me is total or 1, then the influence, then I'm like a puppet, right? If you tell me something, I completely believe it, and your opinion is my opinion. Then, so when you have this kind of property, then you can actually do some weird behavior like this puppet that sort of jumps between being in complete disagreement to being in complete agreement to being in complete disagreement to complete agreement, and this sort of keeps on happening, and they will never reach consensus. So we need to ban puppets, and that's what we mean by puppet freedom. Influences must be under 1. And thirdly, and the one that we're going to go the most deep on, is fairness, which is basically this notion of everyone must participate sufficiently enough, right? And it is easy to see why not having fairness will cause divergence from consensus. See this example, so we have the same network, and we only let agent 1 influence agent 2 by activating an infinite amount of times. This will happen. Agent 3 will never be influenced and will never influence anyone, so you will stay at 1.0 while the other two converge to 1. And this definitely will never reach consensus. So, what is exactly fairness? I said something about like everyone participating in a sort of fair way, but what does exactly that mean? Well, there are multiple notions of fairness. The most popular one in the literature of concurrency being strong fairness, which applied to this case is that all edges or all the arrows must be chosen at some point in the future infinitely often. So let's look at this example, which is a bit country, but I'll get you through why. Basically, we have the same network we've been working on, and we choose edge A, which is to let 1 influence agent 2, then we chose B, which is 2 to 1, then C, 3 to 2, and then 2 to 3, which is D, right? That will be this up until E. Then we let agent 1 influence agent 2 twice, then just 1 B, 2 C's, then D, then 3 times A, and so on and so on. So this is a strong fair because at any point in time, you know that all the other edges will be chosen. That means that everyone will get to talk eventually. This is fair in some sense, right? But the reason why I gave this example specifically is because of its behavior when we plot the opinion values. So look at this. Even though this is fair, everyone gets eventually to talk at all times, they do not converge to opinion. You get the agent in the middle to dance up and down, and they will never reach a consensus over, or they will never close this gap that is forming between the blue one and the yellow agent.
But it looks like that is closing.
It might, right? It would be nice to see long after. It turns out that we showed that if we can build these things are called runs, that we can build these choosers in a way that they never cross a certain boundary, an arbitrary boundary. So yeah, it might seem like it, but it doesn't. So it turns out that this traditional notion of fairness is not enough for us. It does not guarantee consensus. So we might look up to other notion of fairness, like K-fairness and bounded fairness. The first one is K-fairness, which is basically if you take a portion of size K in the run, every letter must appear on it. So for example, and that's what it says formally, if every window, which is this portion I just mentioned, of a determined size is complete. And complete means that there's every letter in it. So if you take this run, which is ABCD, ABCD, ABCD up to infinity, any portion you might take of 4 letters will have the 4 letters A, B, C, D. So it will be 4 fair because you took a window of size 4. And the same thing for this run, which is ABCD and then 4 times C, ABCD, then 4 times C up to infinity. If you take a portion of 8 letters, any will have the letters ABCD, right? So, and then there's a sort of generalization or relaxation of the K-fairness, which is called bounded fairness, and says that a run is bounded fair if it is K-fair from some K in the materials. So if it exists, then your run is bounded fair. The good thing about this too is that it rules out the counterexample we saw before, and actually we showed that they both guarantee consensus. So those are good news. But it turns out that they might not be as nice as they seem, and we need to see some fairness criteria that actually allow us to see what disadvantages these fairness notions have. So the first one is machine closure, that says that any finite word can be extended to be fair. So as an example, you have the word ABB. I give you the letters ABB, and you have to sort of append things to make it a fair run. But 3 fairness, for example, one of the cases of K fairness, cannot be built from this beginning, right? It doesn't matter what you put after. This window of size 3 does not have a C in it, right? So it is not too fair. Then there is constructed lattice. Let me see. Okay. Then it's constructed lattice that says that a notion must not prevent any action from being taken sufficiently often. And I believe this is better understood as a game, which is called the Masur-Banach game, in where I'm, let's say, trying to make, so I get to choose a finite amount of letters, any how much I like, but it has to end. Because at some point, I'm going to pass my turn to the opponent, which is trying to, let's say, make my run not fair. So if I, let's say, limit what he can do, then it will not be a constructed lattice property. This would be said something like, for example, K-fairness is not a constructed lattice property because you sort of are always playing. So if the agent will say, oh, you're trying to build a 3 fair run, and I'm gonna put 4 8s together, then I ruined your run, and that will be, so I will have to prevent that. That means that I'm sort of limited what the opponent has to do. And lastly, random inclusive, which means that every random word or every random run must be fair almost surely, and here random means independently independently and what do you call it when like distribution is identically and independent distributed generated random word is fair with probability 1. So as a recap, so we have 3 notions of fairness. The traditional one that is very nice because it fulfills the 3 fairness criteria, but does not guarantee consensus because we found some counterexamples, and other 2 criteria that do guarantee consensus, but perhaps are not the nicest in terms of criteria. So we want to look, or we want to find a fairness notion that does guarantee consensus and is also nice in terms of this criteria. And that's why we came up with a new notion of bounded fairness. And we were trying to relax this bounded fairness because it was very strict in terms of this criteria. So we said, let's, instead of letting every window we take to be complete, let's just let the complete windows appear infinitely often. As long as we know that there will be another window, then we're fine. We don't need to have it always. The thing is, to ensure consensus, we need multiple windows together, right? So the formal definition of F-bounded fairness is that M is an integer, it's a natural, M complete windows of size K must appear infinitely often. Let's see this to an example. So this is 2 bounded fair run. So you see, and this is for this model, by the way. So you see, you have the first complete window, A, B, C, D. Every edge was activated, and you have A, B, C, B. Every edge was activated. These are 2 consecutive complete windows. And then you have whatever you want to do, right? As long as you're eventually done and you let these 2 consecutive complete windows appear again, you're fine. This is a 2 bounded fair run.
So I can ask a question. I'm a little bit confused because M-bound fairness refers to M and K. So where's the K coming?
Yeah.
What is K?
Nice. Yeah, good question. Thank you. So basically, as long as this is missing the for some K. As long as as long as there exists a K. This is a generalization over bounded fairness that really has this signal of any K. So yeah, you're right. In particular, for example, here the K will be 4, but then as long as it exists, it's enough for us. So so as we said, this new notion is very nice because it's machine close, it has a constructed lattice property that is random inclusive, and it guarantees consensus for strongly connected property graphs with the condition that the M is greater than the number of edges minus 1. Lastly, we augmented our model by adding the possibility of the influences changing over time. And this is very useful because with turning this influence to a function that could vary, we could model, for example, confirmation biases or any bias, as a matter of fact. Like this example, confirmation bias that says that you listen more to the people that agree with you than with the people that disagree with you, right? And this poses certain threats once we auto this model. As seen in this example, this run is very fair. It is M-bounded consecutive fair. It actually is K fair. And even though with this, we can manage to divert from consensus by turning the influence all the way to arbitrarily close to 1. So we need to bound this to be in between some values in 0 and 1, right? But the good news is after we add this condition of bounded influence, strongly connected graphs, and some notional fairness that we showed potential consensus previously, it also reaches consensus. And that's it, of the results. We plan on digging more within regards to what is the value of consensus actually, to which value they approach to, how fast they do it, so to speak of convergence, and also to apply some article Professor Frank published recently where he characterized biases as families as functions. We want to see how that could play out in our model. And lastly, explore a bit more about this random words and probabilistic um, semantics we might develop for the model. And that's it. Thank you very much. Any questions?
Have you tried to apply this to something, some experiment? Yeah.
Yeah. Yeah, that's a very good question. I wanted someone to ask that. So no, the model we based on is the root model, which has actually been validated with empirical data. So we, at least the group, can be confident that his model sort of grasps some sort of real human or real interaction in general. But besides that, this is the first time we model this model, but we hope we can work further on that. Yeah, that's it then. Thank you very much. Yeah. Now, Juan Fernando Paz is next.
Hi, I'm Juan Fernando Paz, and I'm going to show a new model of opinion evolution in social networks. This is a work with from Valencia, Camilo Rocha, and Luis Eduardo Toan, professors of Javeriana University. Okay, and this performance consists in the presence of our model reaching consensus, some properties of this model to reach consensus. Particular cases of other models presented in the literature that our model captured, and finally some conclusions. This is part of my PhD dissertation. Let us begin defining the domain that is into RK space. And there are vectors with entries between 0 and 1. These are opinion of users in the network of key users. And let A the set of any agents, users in the social networks, and I graph that represents the influence graph. And as Joan explained, this is and an arrow between E and H represents that there exists an influence of J over I with a weight, a terminated weight. And this is our evolution rule that's similar if we make that alpha functions is equal to 1, we have the grid model. Okay? We generalize this model allowing that each user I has its own bias over its opinion from the value of opinion of J user, okay?
Sorry, what is alpha?
Alpha is a continuous function that satisfies these properties. It's a continuous function for each A and J. We can have different alpha, and it must satisfy these properties. First is a positive function. We just regulate, control the influence that it represents a bias. And for each A, there exists at least one J such that this value is extremely less than 1. With this property, we guarantee that there is no pocket. In each interaction, in each iteration, user A consider its own opinion. We guarantee this with the truth.
Can you just give me some insight, because we already have an influence graph, right? So we have an influence graph that tells me how much people influence each other. And on top of this, we have this alpha function. So what's the intuition for how these two things, like what's the, because before the intuition was that the influence graph gave me all the information about who influences who. And now there's this additional ingredient of alpha. So can you give me some intuition for what that is?
What is alpha? Word alpha is a bias that controls the appreciate that I give the value to your opinion. Okay?
Okay, but why not just bake that into the I? Because you already have the I.
And no, A is a constant value that is given by a graph.
So the alpha can change over time.
Alpha can change over time, and for each arrow contains an alpha.
I see, of course. Okay, thank you.
And breaking the sum and make a mathematical trick, we can break the sum and make it a matricial structure. Okay, this is the model with us work. This is a dynamical matrix product opinion vector. And to prove the trick of all our results is use these properties. Okay, alpha gives some properties of this matrix that we can use to prove consensus. The intrice of the matrix N has this form, and here X is a number that's lower than 1. Then this is and every time more than 1. Okay? Reaching consensus. A is a stochastic matrix, and we can find a lot of stochastic matrices in literature, Markov chains, etc. And this is any configurations of opinions. And for this matrix, if we have an arrow, we guarantee that the descent of the matrix is non-zero. Okay? The arrows does not disappear in any direction. And in every time, the self-appraisal of opinion is not zero. Okay, not buckets. And here is our main result. Given any configurations of opinions, we got a network and initial opinion configurations. Given any configuration, a strongly connected graph and or map or evolution group. This succession defined by the distance of any vector to its average tends to 0. That means that in each iterations, I am more and more near that the identity line that means consensus. The trick to show this result is linear algebra and dynamical system topics, because this is a continuous map and we have a matricial structure, and we can find that the eigenvalue, the spectra of this matrix are strictly log greater than 1, and this is a contraction. In each iteration, I get vectors more and more small. Particular cases, and if we make that all our functions alpha are equal to 1, we have this good classical model. If we make that this function of this form, we have the confirmation bias that John explained first test and the last performance. with this parameter to satisfy that there's no zero. Okay. And a recent paper of the Professor Frank says that if we have continuous functions of this difference that satisfies that this division is between 0 and 1, we can reach consensus. If we make this, we define alpha like this, we can capture these behaviors. But we can capture any more behaviors. I'm going to show you some examples. Consider a new confirmation bias. Suppose that I have 3 bins, okay? And Republicans, Center, and Democrats. The confirmation bias last function says that the appraisal depends only on the difference. But we now go more and say that the confirmation bias does not depend only on the difference. Depends too of the bins where you are and where your neighbor are too. Okay? Then we make this product for this factor. The appraisal of x to y is a value given by a function that we construct, depending on the number of bins and the minimal appraisal that we want to do. For example, suppose that my minimal weight is equal to 0.01. For x in the first bin, we will give these weights. 1 to the individuals that are in the same bin. It is lower to the next and lower to the next bin. Okay? Then I can consider your opinion, but it's so weak depending on the distance and the bin. The last model cannot capture this behavior. And consider an easy example of a graph, strongly connected graph. We have 2 users, one influence 2 with this weight and 2 influence 1 to this weight. And we have these behaviors. They are continuous functions. This function is oscillating, and this function depends only of x. The other models cannot capture this. And this says that when y is in extreme side of the interval, its value is so low. If y is equal to 0 or 1, its value is low. And doesn't mind the x opinion. This is the identity line consensus, x1 equal to x2. And if we start here in extreme position, x1 equal to 0.1 and x2 equal to 0.9. In fast time, I reach consensus. We can see this in time. The blue orbit is x2 and your red line is the x1. In conclusions, we have designed a model which generalizes several opinion models reported in the literature. And the self-appraisal and connectivity of the graph are crucial to reach consensus. And the new model allows us to capture some behaviors that previous models didn't. Okay, and there's so many questions.
Any questions?
Is
be used for Cambridge Analytica. The escala of Rome.
Pues esto es una teoría. Generalize some of the things
Let's say that it can be used to.
So just to answer this question, yes, it can be used to model like social, like evolution of opinions of social networks. If you knew the influence of some users over the others and so forth, yes, you can use this to model like how opinion evolves. Obviously as an abstraction. And to capture the influence is very hard. There are some work on how to compute the influence of one user over another. For example, in Twitter, you count the retweets. So you retweet a lot another person, chances are that you tend to be influenced a lot by that other person, for example.
And because something like that is the same thing, no?
Yeah, any social network you have interactions.
I have a question. So, I mean, this also applies to the previous talk. So I enjoyed both these talks, and these are really interesting results and interesting models. But you keep talking about consensus, yet we live in a world in which we don't have any consensus. So, I mean, I wonder why your consensus seems to be like the property that you always focus on, and maybe I don't know. I mean, what other properties about social networks do you study apart from consensus?
Social networks are strongly connected. And there is a study that says that the distance between two users are less between 3 or 4. Being strongly connected. But the evolution properties are not this. And there is this dynamical edge, and there are people that just not listen any other. If we see the alpha functions cannot be 0, and the real practice, there's some cases in influence 0.
Just one thing that maybe you mentioned it, but maybe it's a stupid question, so I didn't understand it. It was my fault, sorry. Just, for instance, in the previous talk, we saw that the way you update every round, you could have this synchronous and asynchronous updates. Can you also model both here, or?
I think with Professor Frank, we are working in this. We believe that we can model this by composing n number of interactions, but this is working.
So at the moment it's asynchronous, so you update them all at one go.
Yeah.
Okay. No, that's fine. And how about these kind of properties that fairness? It will apply also here, right?
And there is every edge is activated in each interaction. Synchronous.
All right, so you, that's my question. No, of course, sorry. Sorry. Thanks.
So you have the matrix representation. So I didn't quite get like what are the useful things of representing it.
And this is the main aspect of this work. The matrix of representation allow us to use spectral theory. That is the key aspect to prove these results. And there exists for each matrix a set of numbers called eigenvalues that give us some information of the matrix. Okay, if these eigenvalues are all less than 1, the matrix is a contraction. And it's to say the vectors, when I apply the matrix, the dimension, the magnitude of these vectors are reduced. And this gives us the convergence. Okay?
question? Okay, thank you. Nos vemos mañana, 10 de la mañana, otra vez para el refrigerio. Entonces, venga. El refrigerio debiera para 80 personas. Estoy muy orgulloso de ustedes que hayan acabado. Ustedes son como 30 apenas.